Is the online stuff okay? Okay. Okay, it's 8:45, so we'll get started, and people can trickle in. And again, thank you very much for joining us on this day of celebration, and welcome to NCAR. And I know that some of you have been at NCAR now for or this is your fifth day, because this is the fifth day of our series of workshops. And I just wanted to remind everybody, hopefully everybody knows why we are here. We are celebrating the 50th anniversary of the NSF NCAR's Oceanography section, and we're also celebrating senior scientist Frank Bryan's accomplishments over his 38 years with NSF NCAR. So I just wanted to start with reminding everybody about code of conduct. And please, during your discussions or presentations, offer constructive feedback, share the air, show appreciation and knowledge, acknowledge teamwork, listen to understand, communicate context, and value new ideas and encourage innovation. I wanted to also thank our sponsors, in particular UCAR President's Office, NSF NCAR Directorate, and CGD Directorate for the financial support in the form of discretionary funds. So I just wanted to make that clear. And I wanted to also acknowledge administrative support. I don't list all the names here. Elizabeth Faircloth and Daniel Sena, along with Teresa here and Bonnie outside. So thank you for your administrative support and logistical support. And again, I wanted to thank everybody here, all of you, for joining us. Okay, so when I looked at back in, so the foundation day, I believe, sometime in September, October of 1974, I believe, for the oceanography section. And oceanography, when I say oceanography section, it is literally the oceanography section for entire NSF NCAR and UCAR. We are the oceanography section. So I thought that I would put this thing up, what happened back in 1974. And some of the things are quite interesting because they were worried about inflation at that time as well. That's big sort of worldwide inflation causes dramatic increases in the cost of things. A new house was only $35,000, which is a bargain now. A new car is $4,000. Movie ticket is $189. Gallon of milk was a lot more expensive than a gallon of gas. 42 cents for gas, and milk is $1.39. And postage stamp was only 8 cents. So anyway, this is sort of a joke, I guess. That's the 1974 thing. Okay, and then as you noticed, we had to shuffle the agenda a few times to accommodate time constraints or people's commitments. So this is, I think you all have the current most up-to-date agenda. It's rather full. Most of the presentations, excluding remarks, are mostly allocated for 20 minutes. But I would appreciate if you can maybe stop around 15 minutes, 16 minutes, so we will have time for questions from the audience as well. There will be some remarks initially, and then we have another remark session for about 35, 40 minutes towards the end of the day. So if anybody would like to say something, you can do that during that period. And then our last closing remarks will come from Frank Bryan. Maybe 35 minutes, maybe 10 minutes, we don't know. Then we'll have a reception in the ML cafeteria. We couldn't trust the Tree Plaza or Boulder weather rather, so we moved it inside. So it's going to be in the cafeteria. So with that, I would like to now pass the microphone over to Tony. Tony is the president of UCAR. I think I need to end show somehow, and I lost my, okay. Okay. Here you go,
Thank you, Gökhan. Good morning, everybody. As a card-carrying oceanographer, I have to ask, how many of you in the audience have a shellback card? All right, the rest are polywogs. Okay, great. All right, those can figure that out. So, good morning, everyone. It really is a great pleasure here to be here this morning and help kick things off today. It's a special treat for me to see so many friends and colleagues looking across the audience. So, welcome back, Peter, Jim, of course, Detlef, Eric, Anne-Marie's online at some point. And thanks to Gokhan, Gustavo, and everybody else for arranging this fine event. I think the subtitle for today's event should be Standing on the Shoulders of Giants. My familiarity with oceanography at NCAR actually predates the formation of the NCAR oceanography section and goes back to the summer of 1972 when NCAR hosted the Mid-Ocean Dynamics theoretical panel for about 10 weeks that year, led by Alan Robinson, Francis Bretherton, Nick Fofanoff, Dennis Moore, Peter Rines, and many others. And that provided the theoretical underpinning for the mode and polymode experiments that followed. And then about 6 years later, Dennis Moore founded the Equatorial Theoretical Panel that had a major role to play in accelerating ENSO research. Then if my dates are correct, about 2 years after that mode theoretical panel summer session, Bill Holland started here in 1974, Jim McWilliams the next year, Bert Sepner joined in 1976, Peter that same year, 4 years later, Bill Large, 5 years after that, Frank Bryan, who joined in 1985 with, as just mentioned, 39 years of distinguished service. 2 years later, Gokhan, and the tradition continues. Marika joined in 1999, et cetera. My first trips here began in 1979, doing my computing on the CDC 7600 and the Cray 1, as a good part of my master's and PhD theses were done on the machines here. To this day, I still have my box of punch cards on the bookshelf in my office. And I recall somewhat fondly staying at the Lazy L Motel when it was on 28th Street, working down in the Carrolls to all hours of the night and early morning, watching the little TV monitor for the jobs to finish in the queue above me and waiting for all these expert jobs to finish. Those were Bert Sepner's jobs. And then waiting for my box to arrive. It was my little film box. Let's see. My little film box with 35 millimeter animations of equatorially trapped Kelvin and Rossby waves and illustrating the problems I had with my open boundary conditions at the time when we had open boundary conditions. And then I also recall walking the halls upstairs, somewhat starry-eyed, seeing the offices of the luminaries in our field. Then later in the 1990s, I started to use and work on a sigma coordinate model that Peter and Mark Kane developed. And so to come back here as UCAR president is really a special privilege to me. So if I look back at the history of numerical oceanography and ocean modeling, be it QG modeling, early models of the Gulf Stream, ocean general circulation modeling, thermohaline circulation modeling, ocean mixing, role of ocean eddies, coupled modeling, sea ice modeling, decadal to centennial ocean circulation, the role of the ocean in the coupled climate system, and that list goes on. This was and continues to be if not the world leader in ocean modeling. And a lot of credit for continuing that tradition goes to Frank's leadership over the recent decades. So to close, I thank all of you that have participated in this exciting ocean voyage, and thanks for all your contributions and participation today.
Thank you very much, Tony. So Everett Joseph, NCAR director, could not be here today. He is on travel. So our next remarks will be from John. John is the CGD director. You can either use the microphone or that one.
I'll use the microphone. Thank you, everyone, for coming, as Tony has said, and it feels funny me standing here with all these great names in oceanography here and all the great work that's gone on and the length of time that I've been here. But as ever, it is traveling, and CGD is the home of the ocean in NCAR. It seems sensible that I should stand up and say a few things. As a non-card carrying, no, as a non-oceanographer, I may be carrying a card that says I'm not an oceanographer. I thought I ought to perhaps start with a joke. And then I realized I didn't understand American humor because I was watching this comedy this week. It's like some debate thing, I think, anyway. But so my original joke, I'll tell you in a moment, but my new one is oceanographers eat pets. I don't know whether that's funny or not. No, as I said, I've got a background in atmospheric science, and I often used to joke that to land and ocean teams that I worked with, because I looked after ocean teams, both here and landing and in the Met Office, and I'd always tell them it's just a boundary condition, and of course it's not true, and we kind of, I was always told back, oh no, the atmosphere is just a well-mixed boundary condition for the ocean and land to talk to each other. So, and I'm beginning to recognize that in some ways. So, the ocean and, its role in the carbon cycle and the heat exchange and everything is so important for a system and a system prediction that it's critical and important that NCAR does this work here. And I know that sometimes there's been debates over the years with NSF and others about where ocean work sits, but it's without question that it needs to sit here. So as I said, I'm new to CGD. I've been here for 1 year as of last Thursday, so I'm learning all the time and learning about things. Frank's been here 30 years. I miscalculated. I put 37 years in my notes, 38 years, and so I've got some catching up to do. I don't know how you do that. I don't know. And the ocean section's 50, so I am actually older than the ocean section, which is. I don't know whether that's a good thing or not. But this is about not just the 50 years of the ocean, but about Frank as well. And so Gökhan sent me a few notes, which I'll just go through. But I'm sure through this, you're going to hear all about the ocean section in much more detail and about Frank and some of the things, his achievements in more detail through the talks, particularly Peter's talk that's coming up, I think, focuses in on the history of the ocean section. So Frank started in 1985, so it's probably why I didn't do my calculations right, and as an ASP postdoc, and was an early member of the section in 1987. He was involved in the early days of CSM, which was called CESM, which was called CSM, but people don't pronounce the E, so I think it's still got the same name. And then he was working on quite a diverse range of things that you sent me. So high resolution simulations going to Japan, and then bringing all the data back on tapes. And I made a note that I think perhaps that's probably still the quickest way to transport data if you've got a lot now, taking tapes backwards and forwards. He's done things ranging from the angular momentum of the Earth through to the emergence of natural helium isotopes. So that's quite a diverse set of things as well. So, and so basically, that's all I have to say. I just wanted to thank Frank, myself, because he's a key part of CGD and all the things that he's done. And on behalf of Everett, thank him for all the work that he's done for NCAR. And congratulations to everybody in the ocean section and everyone that's been in the ocean section or worked with the ocean section as it celebrates its 50th anniversary.
Thank you. Okay. So our next speaker is Jim Hurrell. For those of you who do not know Jim, he was a former director of CGD and a former director of NSF NCAR, and now he's a professor at CSU. You can use that one too if you like. It's up to you.
Okay, yeah, can I do that?
Yeah.
There we go. I think we're on. Okay, thank you very much. And like Tony said, it's great to see so many familiar faces here. And I want to begin by thanking GoCon and all the people who put this event together. It's a real pleasure to say a few words on this 50th anniversary celebration of oceanography, and to also say a few words about my long-time colleague Frank and friend Frank. I also want to acknowledge, before we get going here, Marika. I had a great opportunity to sit down with Marika and Bill Holland and go through the history of the section. I actually had some slides on that, but thanks to the Google Doc folder, I looked at Peter Gent's talk, and there was a lot of overlap. So I'm going to kind of skip some of the longer-term history of oceanography here. I just want to start off that, you know, I've had the great pleasure of spending much of my career here at NCAR as a research scientist in CGD. Almost 30 years in CGD. And over that time, I've had so many great opportunities to work with my colleagues in the oceanography section to talk about climate variability and the role of the ocean in climate variability and climate predictability and climate change. And also the opportunity, another role that I played was as chief scientist of CSM. And so I had an opportunity to work with the really talented and dedicated members of the oceanography section on what we now call CESM, which is a community tool that I think is one of NCAR's most significant and impactful achievements. And I want to start off my comments by emphasizing that I don't think CSM would have come about if it wasn't for the vision and the commitment of so many people in oceanography. So what I thought that I would do in these comments today is talk a little bit about my views of how oceanography has fit into the NCAR vision and the NCAR mission. I'm not going to read this. This is the vision and the mission statement from the current NCAR strategic plan. And what I want to try to emphasize and speak to in just a few moments is that, you know, part of what NCAR is about is indeed national and international leadership and research to understand the Earth system and its variability, to support, enhance, and extend the capabilities of the broader community, but also to serve as a vibrant intellectual hub that convenes people from around the community to talk about how to advance science and the importance of the work that we all do. And on this last point, when I think about the history of oceanography, when I came here in 1990, I guess oceanography was about 16 years old, or yeah, so I've lived through a lot of that history. But one of the things that strikes me is the long list of really distinguished visitors that have come, many in the room here this morning, for extended periods of time to work with us at NCAR, to visit the oceanography section, but really all of CGD and all of NCAR. And this collaboration with universities and with other national and international research labs like GFDL, and really the international ocean community, I think, has really been at the core of the oceanography section throughout its history. In terms of research and national and international leadership in research, so much work to be done. I was going to try to summarize some of this as an impossible task in understanding detailed ocean processes and how to best represent those processes and in regional and global ocean models. So much research on interactions between the ocean and the atmosphere across timescales and the importance of these interactions for predictability. So I just want to briefly mention a couple of papers here that I'm sure in this audience you're all very, very familiar with this. The first is the paper that Peter Gent and Jim McWilliams, and I know others were involved, that they published in JPO in 1990, which introduced the Gent McWilliams parameterization of the effect of mesoscale eddies on the mean flow. And it was first implemented in a model, I think, by GoCon together with Jim and Peter and described in a journal article in 1994, where they showed that the model with GM was stable over something like a 10,000-year integration, and no horizontal diffusion at all was needed to keep it stable. This parameterization form has really stood the test of time, and is still used in a large majority of the ocean models, and I think nearly all of the coupled models, if not all of the coupled models, for instance, in CMIP-6. So a really significant contribution from the group here at NCAR. And the other is this K-profile parameterization, KPP scheme that Bill Large, who's in the back, together with Jim McWilliams and Scott Doney, the first ocean vertical mixing scheme that had been designed and tested for use in all regions of the global oceans. And together with these two schemes, with a whole bunch of other work, of course, was put into version 1 of the climate system model, the community climate system model, and it produced the first coupled climate model simulation ever to maintain present-day climate in a control run without flux corrections, and that was a really, really significant achievement. And finally, I just want to say a few words regarding the NCAR mission about the role that the oceanography section has played in so many major field campaigns, international, observational, as well as modeling programs. So I'm not going to explain what WOS is. I think this audience knows a lot about WOS. But in doing a little bit of research for this presentation, I came across this article in 1985 from the Bulletin of the American Meteorological Society. And of course, an experiment of the scale and the magnitude of WOS requires a lot of planning. And this is just a document talking about some of the planning activities. And I know it's hard to read, but what I underlined here are the names in red of people who were in the oceanography section and involved at the very beginning of WOS in planning a lot of these activities and stayed engaged throughout WOS. So many members of the oceanography section here at NCAR. And another example, and I'm not going to give any specifics, but I had to put this in since Detlef Stammer, the chair of the JSC, is here today, is the World Climate Research Program. So many activities within WCRP, the CLIVAR program. Steve Yeager is presently the co-chair of the Decadal Climate Prediction Project. The Working Group on Ocean Model Development, Frank Bryan had involvement in that. GOCON has been a member of that forever, I think, and former chair of that. Bill Large, the role that he played in maintaining and developing the surface forcing data sets for the core experiments and the like. So the salient point here, there's many, many examples, but just that oceanography section researchers have always really taken on extensive service and leadership to the broader community. And then within NCAR, I mentioned what is now the CSM, you know, oceanographers here at NCAR have played critical roles, not only in the science, but in the leadership of this relatively complex community activity. And so at the top there are three CSM chief scientists, Peter and Marika and GOCON. Those three have also received Distinguished Achievement Awards. In the bottom, you see Keith Lindsay and Bill Large and Steve Yeager, who are also recipients of that. And I think I saw Bill Lipscomb. I know Bill Lipscomb received this award as well when he was at Los Alamos, and I want to call him out. Okay, so I'm going to wrap up, but I want to say a few words. Like I said, I'm really honored to be able to say a few words about Frank, who I guess came here 5 years before me as an ASP postdoc and 3 years before me as a ladder track scientist in the section. And I'm really honored to be able to call Frank not only a colleague, but a friend. The field really took notice of Frank, I think as many of you know, very early in his career with his highly cited dissertation work and the resulting journal publications that came out of that on the strength and stability of the thermohaline circulation. And I think this work can be said without exaggeration to truly be seminal work in ocean and climate modeling. In fact, Frank's early work on this topic can be credited with setting the stage for all the research that has come since, thinking about the overturning circulation, the possibility of abrupt climate change, the importance of freshwater impulses. It really was the pioneering study for all the subsequent hosing experiments. Beyond his dissertation work, and Detlef's going to talk about this later today, I see, He really established himself in the field through his conception and planning and execution of the community modeling effort, the high-resolution computer simulations of the North Atlantic circulation that really represented some of the first realistic simulations to explicitly represent ocean mesoscale eddies. CME became part of WOS. There were many, many other publications that came out of this work, PhD dissertations and the like, and I think Frank deserves much of the credit for leading that effort. In fact, he's very well known as an international leader and expert in modeling the global ocean at high resolutions necessary. I actually had a research result from my group in a paper that's coming out in Nature looking at the western boundary current regions and showing their influence on the atmosphere. But I took it out because of time. But the reason I'm saying that is because I have my students read several of Frank's papers. And finally, I just want to conclude that, community service roles, Frank's involvement in WOS and WCRP and US CLIBAR and so many other things. He was editor-in-chief of JGR Oceans. For any of you that have taken on such roles, you know the tremendous breadth of knowledge of ocean sciences such a role requires, as well as strong diplomatic and organizational skills, and Frank has always possessed that. So in terms of NCAR contributions, already we've said numerous things, Frank's role in CESM. This is an early tech note back from 1996, which reflects Frank's proposal of the basic hub and spoke architecture of the flux coupler. And he's been so involved in the Ocean Working Group and whatnot. And this is my very last slide. And it's just to also call out the fact that Frank took responsibility for representing the interests of the broader community in the planning and procurement of supercomputing resources, both at NCAR and at national levels. He was the lead of these two very important reports, the Petascale Collaboratory for the Geosciences. And if you're not aware of this, it's really these reports that laid the groundwork for the NCAR Wyoming Supercomputing Center that we have today. So Frank has done so much, not only for NCAR, but for the broader community. And I truly extend my appreciation and my congratulations for everything you've done, Frank. So thank you.
So now we'll have Peter. You can pass the microphone. Thank you, Jim. So Peter is a retired Ocean Section member, and he'll be talking about,
Can we get rid of this?
I don't know, is it possible to, no, it just shows up in different places. It's random.
What?
It has been there in different places. It's bigger this morning. So
At least it hasn't covered my name. So there we go.
it's on, right?
Is it on?
Yeah, it is on.
All right. So, the Oceanography section, 50 years old. It was formed in August 1974 when Bill Holland on the left, Jim McWilliams in the center, came to start the Oceanography section. And at that time, Francis Bretherton on the right was the NCAR director. Now, I was always told that the decision to have an oceanography section here was taken actually before Francis became director, but having a director whose background was in oceanography, I think cemented the deal that there should be an oceanography section at NCAR, and it was started just over 50 years ago with Bill Holland and Jim McWilliams. In the summer of 1976, Bert Sempner arrived, I believe, in June, and I flew from England on the 1st of September, and my first day at NCAR was the 2nd of September. I retired 6 years ago, but wow, 48 years. I guess I've done a little oceanography in that time, and I've done a lot of bird watching. When I retired, I said to Joni Kleypas, who had the office next to me, well, now I can go and chase rare birds in Boulder County as soon as they show up. And she said, Peter, you've been doing that for the last 40 years. And she was right. So, in the summer of 1980, Bill Lodge came, joined the section, and Francis Bretherton stepped down as NCAR director and joined the oceanography section. Now, it's never been quite clear to me whether Francis stepped down because Bill Lodge arrived on that same year, or whether there were some other good reasons. I just think he'd had enough of being director. Now, in 1981, Bert Sempner left the section, but he left behind a couple of quotations that I want to tell you about. He and I did a heck of a lot of hiking and climbing the high mountains in Colorado. So Bert was always thinking that NCAR really meant the National Center for Alpine Recreation. But my favorite quote from Bert is the following. At some point, there was being arranged a oceanographic meeting in some far-off distant place. And I'm sure Bill Holland was going to it, and maybe Bert wasn't. Anyway, Bert said it was going to be a brief oceanographic occasion for necessary discussion of geostrophic gyres and large eddies. He thought it was going to be a boondoggle. That is my favorite quote from Bert. So Bert left, and in 1982, Dale Hegvogel joined the section. So this is the oldest photo I have of the section. So it's not showing up.
No, that won't work.
This is my own, and it's not working.
You have to use this one.
This one is very difficult to use, as pointed out by Koken.
Well, yeah, right here, actually. You can see it right there. You have to push the top one. Yeah, right.
So this is Dale. Hegvogel came in 1982. Nancy Norton, who was a programmer, mostly with Jim. This is Juliana Chow. Fortunately, we're going to have a better picture later, who was the programmer for Bill Holland. Craig Kunitani, Jim McWilliams, John Masterson, Sally Hawkins, Bill Holland, Bill Lodge, Jim Leuchten, who was a visitor from Woods Hole, Francis, and I guess that was me. So, yeah, that was that in 1983. We all look a lot younger than we do now. Now, Dale, oh no, here we go. The guy of the moment, Frank. As already been said, he joined as an ASP postdoc in December 1985. So he's been here for 38 years with distinguished service and been a great colleague to me in the ocean section, done a lot for oceanography and in particular for the oceanography section. Now Dale Hegvogel left and went to Rutgers in 1986, and a short time after that, maybe in 1987, Frank came on as a scientist in the section and has been a scientist in the section ever since. So the next photo I've got is from the section in 2002. Is this working again or not? Patience is not one of my...
Oh, there you go.
Still not sure how to do this.
Yeah, there you go.
So, that time, here's Matthew Hecht, who's in the audience here. Here's Gökhan, who had arrived in 96, is that right, Gökhan? 92. Bill Large, Nancy Norton, Steve Jane, who's also here as I guess he was a visitor at that point. Keith Lindsay, Esther Brady, Bruce Brigleb, Steve Jane, Steve Yeager, thank you, Brian Kaufman, and Frank. Also, though not present during that time we had a meeting, were two important contributors. This is Joni Klapus, who's not here now, probably in Costa Rica. She works a lot on coral reefs. And this was Scott Doney, who Keith told me yesterday arrived in 94, was that right? 91, thank you. And actually left to go to Woods Hole not long after this photo was taken. Here's Keith, this lady Julie Schramm, Bruce Brigleb, Steve Yeager, Brian Kaufman, a programmer, Jan Moselle, and Frank. And it's absolutely never ever been clear to me why some old photo of Akira Kasahara trying to mount computer tapes is in the middle of this, but, yeah, but it is. So I can't do anything about it. If I cut him out, I cut virtually everybody else out. So anyway, Akira was a nice guy. So Juliana Chow, I'm not quite sure of the date, but Frank gave me this photo earlier this week. She retired around, in the start of the 2000s. So this was an occasion to celebrate her contributions. She came on the section very soon after it was formed. So she'd been there probably since late 76. There's Frank, me, Bill Holland, and this is Maurice Blackman, who was director of the climate division at that point. But this is another better photo, actually, of Bill and Juliana. And Frank's got something in his hair here, but who knows? All right. So the next photo is 2011. So there's a few characters here that need to be introduced. This is Marcus Jochum, who was with the section for quite a number of years. He left and is now at the University of Copenhagen. This is Mary, who I cannot remember her last name. Thank you. I can remember this guy's name. This is Matt Long, who was with the section for a long time doing great stuff on biogeochemistry. Excuse me. Marika, Steve Yeager, Susan Bates, Nancy Norton, Alicia Karspeck, who was with the section for quite a number of years, Bob Thomas, Joni Klapus, Keith, postdoc visitor, I can't remember the name. Thank you. Bill Holland, Brian Kaufman, me, David Bailey, Frank Bryan, Bruce Brigleb, somebody, Gökhan, and a couple other people, Japanese visitor there. So that was the section in 2011, and at this point, everybody doing sea ice modeling was actually in the section. The same was true in 2017. And there's a few more characters who've arrived by this time. Alicia Karspeck, Marika, Laura Landrum, Gustavo is Here by then is Brian Keith. Now, yeah, there were a few interlopers here at that point. Alistair. Keith was over there. I had this guy's name, Enrique Chichester from Rutgers. Dan Witt was here. Scott Bachman, Steve Yeager, Dave Bailey, Matt Long, Justin Small was over there. And so that's the actually the last photograph that the group's taken. And since then, all the sea ice and other people, Dave Bailey, Marika, Laura, have actually abandoned us and gone off into their own section. So this was 7 years ago. So my proposal is that today, as well as having a photograph of everybody who's here, we should get together again and have another photograph to update just the oceanography section. So that's it. Thank you.
Any history questions for Peter? Thank you, Peter. So our next speaker will be Bill.
It's amazing.
And it's on already.
Oh, thanks. Yeah.
Absorbs the green.
So you've seen lots of, is this the
Oh,
microphone?
you have it, the microphone.
Oh, right
already.
there. So you've seen lots of changes, but one thing that has never changed is this has never worked perfectly. And especially pointers, even your own. So yes. So I wanted to talk to you about something I don't think anybody else could talk to you about. And that was the ocean instrumentation and development of the 1980s at the ocean section at NCAR. Anybody else can talk about that? Now, unfortunately, that leaves Frank out because he wasn't here at the beginning and he was wise enough never to get into this business. So I apologize, Frank, but I'm just going to stick with this part. So this is an extinct branch of the NCAR ocean section evolutionary tree. However, I hope you will see there were some lasting legacies. I'm one. I came here in 1980 to do ocean instrument development and deployments, and I'm still here. But ocean instrumentation and development is not. So I'm one legacy. I'll show you some others. You can decide whether these are for good or for ill. So that's basically what I'll confine myself to. So let's talk about the developments. The developments that were going on were basically an effort by Jim McWilliams to get into ocean observations. It was even more than that. He formed this program called Drifters, which was a way to get money out of NASA, but it was also to coordinate national drifter and float developments. The big thing to come out of that program was that's where they defined floats as being neutrally buoyant and drifters that float as being things that drift at the surface. It was always backwards to me. I never did figure, but once that group decided that's the way it was going to be, that's the way it was. And it was quite a group. So particularly what I was brought in to work with was an NCAR Oregon State proposal for 18 months. It was Jim McWilliams and Peter Neeler, a quite interesting pair of bedfellows that I can't tell you how wonderful it was to work with them. And interesting as well. The group dynamics was fascinating, but the scientific effort and capacity was truly remarkable. So eventually Peter Neeler went to Scripps, leaving another great house in Corvallis empty. So what we were doing is deploying what we call climate air-sea interaction drifters, or CASID drifters. I actually brought one here once. And that's what we were doing. I also worked a lot with Peter on mixed layer drifters that went from window shades. That was the old Figgy drifters. They went to Holy Sock drifters that John Dolan at MIT had, to TriStars, which Peter pioneered at Scripps. So that's sort of the evolution of mixed layer drifters. Other things that were going on in that group were all the Woods Hole engineers. The good ones were Bob Walden and Henri Berthaud and Doug Webb were all part of the drifters group. And that was forming at that time the Alice floats, which became Pallas floats, which became Argo floats, which then became Argo, you name it. They do everything. So that was all part of the drifters program. And then there was something called the Flying Fish. This was, they didn't want to stop ships for CTD, so they just dumped them off. Down they went, and then they would glide themselves back up and jump into a net being towed behind the ship that never had to stop. And you can see pictures of this thing flying. So that basically gave room to gliders, that you could actually steer these floats and stuff. So that was eventually became gliders. And also another thing we were doing at the time, a lot of this had to do with Francis being around and myself on scatterometry. We did work on NSCAT, the NASA satellite KU scatterometer. And you see, it's 1985 to 95. Now, the wonderful thing about NSCAT was it never flew. But the program kept going, so the money kept coming. But it never flew. It actually became a Japanese satellite called Adios, which went adios. It was up for a very short time, and then the solar panel wire broke, and the solar panel was in a big ball at the end of this big beam, and it had no power. So that was short-lived, but the funding lasted a lot longer than the satellite, and we I think did some nice things with that. So that's kind of the development of instrumentations that was going on here. And the deployment side, these are some of the experiments we deployed in, okay? There was the Storm Transfer and Response experiment in 1980. That's what I came back for and had a wonderful, all expenses paid trip to Ocean Weather Station Papa. If you haven't been there, don't go. It not only, it's just like any other piece of ocean, except it's rough. The waves when I was there were 75 feet. And what do you get after a 75-foot wave? Another one. And then another one. That was quite unpleasant. But anyway, that was Strex in 1980. Then there was the frontal air-sea interaction experiment in the Sargasso Sea in 1986. That had other NCAR aircraft and things deployed on that one. There was ocean storms in 1987, 88. That was again back at Ocean Station Papa. And then we've heard some things about what we did with WOS. But I wanted to point out that both FASCINEX and Ocean Storms were outcomes of a February 83 ONR, of all people, sponsoring a workshop here on air-sea interaction. And ships sailed because of that meeting. And one of the more interesting people in drifters and in oceanography is Russ Davis, actually thought that was one of the better meetings he had ever been to. And that's not easy to get that out of Russ Davis if you know him. So that was the deployments, and that's where those big experiments came, and many ships sailed. And I wanted to show you some results from Strex. Ocean Storms were similar. And these were the Cassid buoys we deployed. Okay, they were basically floating thermistor chains. And they weren't small, they were a couple of meters long. And the big thing was, at the top, you see a port. That's for a barometer port and a barometer inside, because that's the MET measurements, which you then use to argue that people want them because the MET surfaces want surface pressure. So you had to put that on. You didn't use it for oceanography, but it paid the price of the transmitters and getting onto the service Argos and GTS and everything else by sending that. So then we started to send the things we really wanted, which were, there was an SST sea surface temperature sensor on the float itself. Then there were 10 subsurface temperatures to 120 meters, 3 subsurface pressures, because the shear would drive these, would make these lines curve. And you could actually, from the pressure sensor and the difference in pressure derive. I wish I had AI at the time. I did it by hand, and it took months. But we could get shear out of those, out of the curvature of the wire. Okay, and these all came through Service Argo as a data transmission, very limited, and also did the satellite positioning, which gave you the mean current as these things drifted, and then you had the shear underneath. So what we eventually went to put on these things were wind velocity and stress measurements, both, air temperature, precipitation, and air humidity, and we developed some instruments and got somewhere along that line. Precip was neat. We used to do it with acoustic noise. Just listen down below at 200 meters, and then you get a nice spatial average of precip and the whole noise spectrum. You can measure wind speed that way, take the wind speed out, and then you get the precip. And somebody took this over, and the big problem was it wasn't a unique solution. The drop size distribution mattered, and so, but over the ocean, sometimes you could, anyway, he got quite far on that, but it died. Many of these died. I could measure stress off these buoys directly, not bulk formula. That died. Various things, as I say, this was an extinct branch of life. But that's what these Cassid drifters were. And here's the big result that they got. This is a plot of a storm response that we got in Strex ocean storms with both the mixed layer drifters and the Cassids. But what you get is that with depth normalized by the mixed layer depth initially, you got this big cooling up to a degree and a half in 6 hours, which is something like 1,800 watts per square meter cooling, which didn't come through the surface, let me tell you. The surface was actually heating at the time. And what it was mixing down below. And so you got this big heating curve at 1.4 meters maximum. And then from that, you could also get these temperature gradients. So if you have a time change of the temperature and you have a measure of the gradients, you can get a diffusivity. And the diffusivities we got out of this plot have been found again by people at University of Washington, and it's about the same number. So that's one thing we got out of these drifters. But the basic thing was this was quite an explanation for very big temperature changes. I say 1.2 degrees in 6 hours is a big mixed layer temperature change. But the spatial scale was only about 100 to 200 kilometers. 200 kilometers away, you got nothing. So what was going on? So I took this data and gave it to Jim Price, who had just developed the Price-Weller-Pinkel model. And I remember him coming back and saying, I didn't get any, I put your data through, I couldn't get anything. I got no cooling. What? And so that is what led us to KPP. If we thought, well, if he can't do it, we're going to have to figure out what to do it. And the nice thing about going and doing this is we had down at M³ someone by the name of John Wingard. So we brought him up and said, okay, what do you do in the atmosphere? And he's the guy that introduced us to the Troon-Mart ideas of a very simple way of mixing in the atmosphere. And that at the same time was being put into the atmosphere by Byron Boville. It's Alzheimer's. Holzlag, yeah. So they were doing that, and so we put it into the ocean. And as you see on this far side here, if you look at the observed, that's this plot in a different way. It's actually in real depth in one particular event. And you can see how much more we deepen in KPP deepens as far as the OBS, which is to about almost 85 meters. But there you see Meller-Yamada doesn't do very well. Doesn't deepen enough. It's too local. But there you see PWP. And it does not a terrible job. It does a little better than Meller-Yamada. So I said, what the heck happened? And then Price hits his head, hand on his head like this, and he says, I didn't rotate the winds. So that's why he didn't get any deepening, because when you rotate the winds inertially, the energy going in, your winds follow your currents around, your inertial currents, and you just keep pumping energy in, and that's what gets you to deepen. You keep the wind steady, you just get a Pollard-Rimes-Thompson response. It's boring. And if he had done that and got that mixing, we wouldn't have developed KPP. It was only because he said, I can't get it to deepen. And without John Wingard, we wouldn't have been able to do it. He was a real giant and so helpful, and that was that story. So that's a legacy out of this observation of this extinct branch, at least I think. Now you can say whether that's positive or negative, that's up to you. Okay, so it's put these blanks and changes in here. So, okay, WOS was another, I'm calling it a field program, and this is of instruments, not the, you saw things like the CME, I think Detlef said he was going to talk, somebody's going to talk about that. And that was the modeling part of WOS. There was a lot we did, as we saw in the planning of WOS. It was half of my life for a while. And WOS was a decade of planning. It took 10 years to plan it. And I can't tell you how many miles of travel. And basically what I was put in charge was with air-sea fluxes. What are we going to do in WOS for air-sea fluxes? Okay? Now this is global. This is a world ocean experiment. And the idea came up in a meeting in Corsica, talking to Peter Taylor from England, that you could, in fact, he thought you could just use the initial forecasts, the initial condition from forecasts to give you the met parameters to compute bulk formula and get the fluxes. And that was a discussion we had in Corsica. And that actually has an assimilation of all the GTS data. So a lot of data go into that, especially pressure, and it gets it turned into winds and things like that. But then you can, the idea was we could also correct that for biases relative to all WOS in situ and buoy and ship observations, and learn how to correct the initialization of the forecast models. Because don't forget, those initializations would put in biases to get rid of the model drift to get the good forecast. That was commonplace. So we were going to correct, and that was dead on arrival in WOS. And why was it dead on arrival? No WOS dollars are going to go to any med agencies when I'm alive. I heard that, with a few explicatives in there. So that was dead on arrival. There was no way WOS was going to get anything to do with meteorology. So they did other things, and that whole year of writing that report, I think Jim was one of those underlying things in Jim's outline went nowhere. But that is what led to the core forcing, or the OMIP forcing that we came up with here with Steve Yeager. That's where that idea originally came from, was from WOS planning. Now, so what we did in core forcing was actually the global reanalysis. We didn't use the actual forecast data. It was the reanalysis data. And there was NCEP, NCAR, then we went to JRA. And apparently, GoKent's got some funding to go to do it with ECMWF now that JRA is out of the game. So, but it all started back from that meeting in Corsica and some conversations with Peter Taylor. So that's the legacy. Hopefully it's not all bad. And we used all the in situ observations you can find. And most of those were things like the Toga-Tau array and TPOS, and stationary arrays with air-sea fluxes are what did in CASID. Because CASID was drifting Lagrangian framework to do a similar thing, and people liked arrays. That's one reason it died. The other reason was NCAR, that was too much for ATD. They didn't mind doing atmospheric things, but the ocean stuff, no. So we didn't get very far, and then I decided, we actually wrote an STC proposal to put all these drifters and have to move it to Oregon State since NCAR didn't want it. But that failed, which is why I stayed. So, and did KPP. So that's more history. Whoa, was that the end? Okay, so the other thing about WOS, what was I going to say? Oh, yes. So a big part of WOS was also the mixed layer drifters. We put in the mixed layer drifters, and there was a drifter program, and you had to plan everything in WOS, right? 10 years of planning, you come up with plans. But they were grandiose plans. I mean, it was I think 250 to $300 million is what it was going to cost. And all the programs were being cut back and whatever, except the Drifters program, because it was run by Peter Neeler, who was a tour de force, let's say. So he went around to every little country he could find, and he loved to travel, and talked them into putting out a drifter or two, so they could buy into WOS at the $2,000 to $10,000 a year level, because he could get them deployed, or they might deploy them on a fishing boat or something. So the program wasn't being cut, was staying as planned. So I remember Peter and I got hauled off to, and of course, travel's cheap, so we go to England. We're called by the chief scientist of WOS, I won't mention any names, hauled on the carpet and said, of all the programs in WOS, the Drifters program is the only one that hasn't been cut back. You need to cut it back. Can anyone here imagine what Peter said to that? I can't repeat it, but just if it was, because also we have the altimeter now. That'll give a surface current. And he looks and he says, don't you want to know what the ocean's actually doing? And that ended the conversation. The program was not cut, and I think the Global Drifter program went on and on. And that's all due to this kind of chain of which we had a part. And that's the legacy. And it is, as I say, an extinct branch, but we had some good things come out of it. So thank you.
Any questions for Bill? It's sort of the unknown part of oceanography. So, Frank.
Bill, Jus Bussinger came here after you retired from UW, and was he involved in the air-sea drifter work at all?
Yes, in the following. No, I was more involved in what he did. He came and did the PAM stations. So he was developing the flux network for the overland. Okay. So I talked to him a lot. And that was mostly me going there, but he was part of the discussions on the actually measuring the stress. And so we actually got a package built at M-Cubed, or ATD at the time, not M-Cubed, ATD, that actually measured stress directly. And in Fastinex, that's one of the neat Fastinex results I thought that's gone nowhere. We actually had a case where the wind was blowing across the SST front in the subtropical front, and the wave field was quite different because of the currents on one side or the other. And the wind came across and didn't change much, but we had stress measurements on both sides, and the stress just really responded to the waves. And at the same time, we had, because we were part of NCAR, we had a NASA aircraft going off, and there goes the backscatter, just went with the stress. Now, we had done some of this from the old Jason experiment and showed that it correlated better, but this was a direct, I guess, observation and evidence that the KU scatterometer actually measured stress, not wind. So we took that to NASA. That went nowhere because they had to get a lot of data in order to do all their algorithms, especially on wind direction. And so they went to the moorings and got it off the NOAA buoys. But what it means is any data set, and to a large extent, these reanalyses are actually the effect of waves on the stress relative to the wind is already in the scatterometer winds. They call them winds, but they're sort of pseudo stresses, not exact because it's not a direct measurement either. So if you go and take those winds and then put in a correction for waves and stuff, you'll be double dipping. If you take just mooring data, yeah, you're okay. But it's all been calibrated to the backscatter, and that's already in the algorithms for these backscatters. That was another outcome. But that was one of these things I thought was quite an interesting discovery that sort of gets lost, you know.
Any other questions for Bill? Okay. So our next speaker is remote, Anne-Marie Triguier. She's joining us. Thank you, Tony. She's joining us from Brest, I believe.
Well, no, Gokong, actually from Wales.
Oh, from Wales, sorry. Okay. She couldn't be here in person, so. I have your
don't know.
presentation up here, and I
Yeah,
can
so,
stand, yeah, and then just tell me when to forward.
or yeah, we can do it that way, or else I could share my screen, but it's probably better if we do it that way.
You want to share your screen?
Perhaps it would be easier.
Is it possible? Okay, so I'll continue discontinue here. So go ahead and please share your screen.
Share now. And I need to select the right window. Allow, and then make it full screen. Is that okay for you?
Yes, we can see it. Please go ahead.
Okay. Well, thank you very much for inviting me. It's a bit disappointing for me to be so far from you and not to be able to enjoy the celebration as I would have on site. But I am really very happy to talk about how the stay at NCAR and in the oceanographic section and working with Frank has really helped me over the year to got me into some scientific questions and helped me move them along. So I was at NCAR, an ASP postdoc between 1987 and 1989. So at the time that was the NCAR t-shirt design, and I always wondered who the oceanographer was. I don't know whether Bill, it was whether it was modeled after you, but I have, of course, very good memories of that time at NCAR. My son learned to walk at NCAR in 1988. And I have also found this photograph, not very high quality, I'm afraid, where you can see Frank and a few other senior oceanographers watching the Up the Hill race. 1989, and I think there were mainly the women running the race and the men were just watching it, I guess. So what I'm going to talk about today is eddies and meridional transports. I will try to talk about two things. One is mainly the subtropical gyres, and then to a little bit about the exchange between the North Atlantic and Nordic Sea, where we still have many modeling problems, I think. So let's start with heat transport in the subtropical gyre. I don't know, can you see my pointer?
I don't think so.
Okay, so okay. So those two figures are from the CME that you will hear more about, I'm sure, during the day. It's from a Bryan and Holland's paper in AHA Ulikoa workshop in Hawaii. And those are the heat transport in the North Atlantic as a function of latitude in the CME at 1/3 of a degree resolution. And that was, I think, the first time that in such a realistic setting, the eddy contribution to the heat transport was estimated. And Frank and Bill contrasted the transport during 2 seasons, January, July. That was also quite new to point out the large seasonal cycle of the heat transport in the North Atlantic. But the eddy contribution, in fact, was quite small, at most 10% of total. And of course, we know that 1/3 of a degree resolution was not enough. So 10 years later, there was a paper in the WARS newsletter by Frank and Rick Smith, where they had this time again the 1/3 of a degree model, so 1 degree model, 1/3 of a degree model, and 1/10 of a degree model, which is the solid line here. And so they demonstrated that the higher resolution model fit better with the observations, which are shown by the bars, the vertical, and with the uncertainty limit with the vertical bars. And the eddy contribution was tended also to be higher at higher resolution. But really, the fact that the meridional heat transport went up and got closer to the observations at high resolution was really due to changes of the transport by the time mean flow. And the eddy transport didn't change much. And also they emphasize the fact that there is cancellation between the mean and the eddy, because in the eddy flow you can see this big change and this big divergence of the eddy flux near 36 north. But you don't see it in the total, which means that it's compensated by a similar spatial variation of the mean flow. So this question of the cancellation of heat of mean and eddy was not completely new, and it was discussed a lot by Frank Bryan, another Bryan, Frank Bryan in the late 1980s. And Kirk found that this compensation between eddy and mean was to be expected because there was little diabatic, relatively weak diabatic heating in the ocean. And so the eddies were moving heat along, but without actually exchanging it with the atmosphere or without any diapignal fluxes that would have led to a change in the overturning circulation. So necessarily, there was this compensation between the eddy and the mean. Some years later, I came upon a kind of extreme case of this eddy mean compensation that was in NEMO in North Atlantic configurations and global configuration based on the 1/12 of a degree NEMO model. And what I had was, I mean, this is about the same plot as you saw before, the CME plot, but now it's with NEMO models. The pink is a kind of estimate from the forcing of Large and Yeager. So the heat flux that you need to equilibrate the air-sea fluxes from Large and Yeager 2009. Here you have the rapid observation in red. Again, the heat transport at higher resolution, 1/12 of a degree, is closer to the observation than at 1/4 of a degree here. But for the eddy flux, what you notice is, although the 1/4 of a degree model looks a bit like it looked in the CME, at 1/12 of a degree, there is this huge peak in eddy transport at 36 north, which is completely compensated by the mean flow, because you see in the total, you don't see the signature of this peak at all. And so I was a bit surprised, and I look a little bit more. So I looked at the contribution to this peak along a section at 36.5 north. And so this is the section, and this is the color is the contribution to the eddy heat transport in bins of 100-meter depth. And you see that everything is happening in this red spot there. So it's happening near the surface and in the western boundary current. So it's really the western boundary current that's creating this peak. And looking a little closer, what you find in the Gulf Stream separation region, and this on the left are observations from satellite altimetry. So in black, this is the axis of the maximum geostrophic velocity. And in red, it's V prime T prime correlation. And what you see is that the V prime T prime correlation is to the north of the axis of maximum velocity. So there is a kind of asymmetry. And this asymmetry is well reproduced in the model. And the model is probably overdoing it a bit with a very high V prime T prime correlation just north of the Gulf Stream. And so you can reproduce the behavior of the eddy flux just with a kinematic model if you take into account the fact that the Gulf Stream, in the Gulf Stream, the maximum gradient of temperature is not at the same location than the maximum velocities. Maximum velocity is here, and the maximum temperature gradient is shifted to the north. And when you have a jet that presents these properties and you just make it meander, then you get automatically this effect of eddy mean compensation with a V prime T prime that is concentrated on one side of the jet, and that when you integrate over a whole section, you get a maximum of eddied flux there, which is completely compensated by the mean flow. Because obviously, I mean, the simple kinematic model of a meandering jet has no diabatic implication whatsoever. And so you are supposed to get overall, the total flux is supposed to be completely the same as if the jet were not meandering. So this eddy mean compensation is even more prominent if you consider the transparent salt. And this is a recent result from a PhD student, Ophélie Muriot, who was did her PhD at Imperial College. And she plotted the transport of salt divided by a constant so that it's expressed in sphere drops here. So this is the transport of salt in a coupled model from the UK Met Office. MM is a quarter of a degree and HH is 1/12 of a degree. And you have the eddy and the mean, and you see that they almost completely cancel out. The total, which is in blue, is close to zero in the case of the high resolution model and a little less so in the case of the low resolution model. But in fact, when you think about it, in an ocean at equilibrium, the transport of salt would be zero, because at the surface you don't evaporate salt and you don't precipitate salt. So obviously, if the ocean were at equilibrium, the transport would be zero. So what is happening here is that the 1/12 of degree model is at a reasonably good equilibrium, not much drift, but probably this quarter of a degree model has more drift in it. Although perhaps there are also some parameterization effects that come into this difference. But so this is not a very interesting picture, because you see that the eddy is compensating the mean, but you still need to go back and relate it to what drives the cycle, the transport of freshwater and salt in the ocean. And so you can go back to a kind of freshwater view, or you can go back to, you can stay with the transport of salt, but then instead of decomposing it into two parts, mean and eddy, as usual, you decompose it into three parts. So this is what I'm showing here. It's perhaps a little too many curves. Sorry for that. So now we are in the global ocean. So it's a global transport of salt in the 1/12 of a degree model. And the total is the red. So it's reasonably close to zero. Here in the Southern Ocean, it's the effect of sea ice, for example, which doesn't melt at the same place it is formed. And then you decompose it into three terms. So the first one is the thick black line, TM, and this is simply the average salinity over a section transported by the average velocity over the section. So the average velocity is just there to compensate, to close the mass budget and to compensate the evaporation and precipitation. So this total transport by the average velocity over the section is what is balancing, in fact, the E minus P, and you can relate it to the forcing, which is the gray line here, again from Large and Yeager. And then you have the remaining of the mean transport, which is the thin black line, and the eddies. And in this presentation, you see the mean and the eddy not opposing each other, but the mean recirculations on the section and the eddies on the section are both contributing to bring back the total salt transport to zero, to counteracting, in fact, the effect of evaporation and precipitation. So basically, you see in your subtropical dry, there is evaporation. This is by the barotropic transport coming in to compensate the mass budget. Then you get more and more salt, and you need to evacuate salt. And part of it is done by recirculations of the mean flow, and part of it is done by eddies, which is the blue curve there. And you can see that at the boundary between the subtropical and the subpolar gyre, the contribution of eddies and the mean are equivalent. It's almost 50-50. And the same in the Southern Ocean. So what is, I think, really exciting now is to think about how these eddy fluxes will the future. And I show this result of what from Avi, and to as placement, because I am participating in this European project called ERI, European Eddy Rich Earth System Models. But of course, I could have shown probably similar results from CESM, because CESM is was the first model that was run at such high resolution as an eddy rich model for future scenarios as part of the highest project. So here, this is a paper by Nathan Beach in Nature Climate Change, where you can see the change in the surface EKE. You can see a poleward shift of the Gulf Stream that is reflected in the eddy kinetic energy, a contrasting behavior in the Kuroshio. And so I think this is one of the exciting prospects of the next years, is to understand how the role of these eddy fluxes will change in the future. So now, what about the exchange between the Atlantic and the Nordic seas, and even farther north in the Arctic? This was a bit more difficult to do in the CME, because the CME model was a limited area. But all the same, I mean, Klaus Böning tried to evaluate the deep water formation and the meridional overturning in the CME. And you can see that there was this plot where the water mass formation, of course, was occurring south of 65 north, because the boundary of the model was closed there. There was no real connection. Then this was revisited in the POP 112 degree model, but in that model at the time there was no sea ice, so that was also a problem to look at a realistic, in a realistic way at the exchange between the Atlantic and the Nordic seas. And then a little later, there was another paper by Julie McLean, but she found that there was too much ice at the time in CCSM4, I think it was. So now
you have about 2 minutes, Anne-Marie.
Okay, so I will go very quickly. Just say that I try to revisit that heat inflow in the global couple model. This is a snapshot of sea surface temperature. Then that in this study, we could identify 2 hotspots of eddy fluxes in the Nordic Sea, one here for heat coming over Nipovit Ridge, south of Ram Strait, and of course a hotspot of eddy fluxes in the Denmark Strait. This is not a surprise. This is a place known for its eddies. But we also found problems in this model that you can see here with the eddy kinetic energy in the model. No, it's a root mean square velocity, so the square root of the eddy kinetic energy in the model, and from drifters. So drifters that are the legacy of what the programs that Bill talked about. And obviously there is a problem in the model. I mean, the eddies don't get into the interior, and the eddies should be bringing heat into the interior, and this heat should be lost to the atmosphere. And this is not happening in this model. And so do we need to move to higher resolution? Certainly, yes, considering the small Rossby radius at those latitudes. But I think there is also a problem with the representation of flow topography interactions in this case with NEMO 1/12 degree model. So this is my conclusion. I think we have done an awful lot of progress in our knowledge of the eddy fluxes in mid-latitudes. And then with the new high-res MIP simulations, we can project their evolutions in the future climate. And for eddies and flow topography interaction at high latitude, I think this is still a challenge, and which we hope to study in high-res MIP and in Europe with the ERI project. So thank you very much.
Thank you, Anne-Marie. Any questions for Anne-Marie? Bill has a question in the back. Bill Large has a question, Anne-Marie.
Oh, thanks, Anne-Marie. It's great to see you, by the way. When you do your decomposition of the transports of salt, is any one of those or a combination equivalent to what the ship transects compute as freshwater transport? Because somewhere in the North Atlantic, there's a real inconsistency with those, and maybe it's because those estimates miss some of your eddies, and that's what I'm. Can you actually have you decomposed it that way into what people think they observed with a section versus the total?
I mean, I have talked a lot with Lynn Talley about this, and basically what I was trying to do is to avoid freshwater, because I mean, you may know about this paper by Ursula Schauer when she says freshwater is not a useful parameter in climate research, and I completely agree with her. So I wanted to do away with freshwater. So somehow it's a way to recover the same framework as Lynn Talley or others would use with freshwater, but without having to choose a reference salinity, because if you have a section, you just take the salinity average over your section, and that's it. You don't have to have a specific reference. And if you want to compare with observations, you just take the E minus P from observations, and you take the salinity from Levitus, and then you have your transport by the net mass flux, which is then part of your decomposition. And yes, in fact, if you have references of mismatches, because the eddy flux is missing, I would be very interested. When I looked and compare with Lynn Talley's work, in fact, what happens is the section, for example, at 26 North, it's where eddies are negligible. So there is no mismatch there. So maybe there are some sections where you really see that, but I had not found them at the time I wrote that paper.
Thank you. Any other questions? Okay, if not, let's proceed. So our last speaker before the break is Detlef Stammer. He is currently the chair of the WCRP JSC. Maybe we should do it the reverse way, this way. Okay, and it's on.
All right. Thank you very much. And it's a great honor to be here today and given the opportunity to speak. And indeed, I do this in my capacity as chair of the Joint Scientific Committee of the World Climate Research Program, really in recognition of the great, enormous contribution NCAR is really making to climate research and WCRP in particular. And Jim already summarized this, I think, very well. I don't want to go in more details about this, but it's really true that over a long time, NCAR was central to what WCRP did and is still doing, and we still have an enormous amount of contribution, personal participation in WCRP. But the title I gave to my talk is CMC Roles in Advancing Ocean and Climate Models. And to some extent, this is a kind of a personal reflection. I was not here at NCAR until 2014, and so what I will present here is really an observation from somewhere else in the world. Of course, you will see basically it is a story of a career, and I could pick various different careers, but given the opportunity or the occasion why we're here, why not picking Frank Bryan as the career we want to describe? And if you want to describe a career and also motivate the title, you need to go back. And we have already heard that when Frank came here, it actually, let me see if how do I move forward? Next, here. Oh, sorry, backwards. We need to go backwards. So what actually was the situation in this case, the 80s, and what was the state of knowledge, what were the problems we wanted to solve? And Tony already introduced MODE, the Mid-Ocean Dynamic Experiment, and in fact that had happened in the late 70s, an experiment that I guess if you actually go back and listen to the argumentation, kind of let's find an eddy in the ocean. It's kind of strange from a present point of view where we know eddies are everywhere, but the goal was really where can we find, is there a chance to find one? And what you see in this little picture is really float trajectories that were sampled during MODE. Swallow put floats in, and so that was one of the outcomes. Really, there's a turbulent field in this ocean, and how can we explain it? And so this is where the demand came in for new theories, for more observations, for particularly also more model simulations, better model simulations, and more realistic model simulations. And so there is in fact a very nice, almost a movie, it calls it The Turbulent Ocean. And preparing this, I went back to this movie, and this is really about MODE, and also shows, in fact, NCAR's contribution, in this case, to ocean dynamics, to oceanography, and it all sort of overlaps with what we have heard already about the history of the ocean section and when this all came about. And what you see here, in fact, in the upper left panel is probably the path that you all know, that you all did. In fact, being at NCAR, you have to go over this path every lunchtime. And so a lot of ideas apparently had been born there. And this is from one of the planning meetings of MODE, where you see, in fact, Francis Bretherton in the middle. I'm not sure exactly who the others are. But a lot of this planning, and we have heard this already, were done here at NCAR with Francis involved. And then MODE came about, and there was this experiment. You see Francis there, and sort of you can already see from his body language that he is slingering on the ship, sort of finding his way as the theoretician. And maybe I always thought he was a mid-atmospheric theoretician, but apparently he also liked the ocean, but he didn't like the ship. And so that's actually a text he was speaking there. I mean, he wouldn't really stand this for a long time. And then it's also from this movie, if you go there, these are just a few sections, few parts of what they speak. But Francis says here there were also some disappointments. And I, in fact, went back to the movie this morning and listened to, so the disappointment were really bringing the observations together with the theory. So the discovery was there, you can make observations, you can make a kind of, you might have a model, but really bringing this together was a challenge and was recognized as a challenge. And this handsome young man there you will recognize him as Jim McWilliams. In fact, all the pictures we saw today were Jim McWilliams without hair and a little bit older, but this was Jim McWilliams really during the mode period. Again, a big NCAR contribution to oceanography already in the 70s. And so the state of knowledge of modeling, and the call was really about better modeling, better simulation of the real world. This is what happened in the 60s. Really very smoothly, basically we see the gyre circulation. We started to get also boundary currents. CFD, computational fluid dynamics, numerical modeling came about. We have the pioneers, Veronis and Kirk Bryan. Kirk Bryan was already mentioned. This is in the 60s, but essentially limited really by computer power, among other things. And that's where people started to simplify. What can we fit on the computer in this time? How can we actually get results? The QG, quasi-geostrophic modeling, was really one of the outcomes. People tried to use as much as we can these computers that existed, and so we had to compromise. We had to go back and back and back, and I was looking for a picture for quasi-geostrophic model results, and I found this one, which is in fact from Antonietta Capotondi. It's actually from the 90s. This is a work she did together with Bill Holland. This is her thesis, in fact, where she did data assimilation. And so this is already a very good picture of a quasi-geostrophic model. And this is all what I describe here actually happening at a time when I was a student. In Kiel, listening and looking at listening to the discussions, looking at these figures, and as students we were always kind of frustrated about the quality of the circulation. This is already the better one from the quasi-geostrophic modeling. You see the contours. You start to associate this with the Atlantic circulation, but of course it was very limited. And at this time, there was really a couple of things changing. One was there's a much bigger computational capability came along. Cray 2, there's already the Cray 2. Cray 1 was here and somewhere else, but this opened really a new possibility for the computations, for the modeling. This is a pre-VOS period. Bill, this is in the planning phase of VOS. So in the 80s, where it was then decided, let's really go to primitive equations. Navier-Stokes equation, let's do this step. And there was an activity here at NCAR, and there was an activity in Kiel, back in Kiel, where I was a student. And so these two groups started to do these experiments, and that were called the community modeling experiment. Yeah, being a student, of course, we followed the results that came out, and we also listened, and there was always this talk. And in Kiel, it was in particular Klaus Böning involved, and Jürgen Willebrand and others. There was this reference to this person at NCAR, Frank Bryan. I never met him, I never saw him, but Frank was sort of this mystery man on the other side of the Atlantic, doing this work. And so together, I think there was then the results coming out of this primitive equation model that suddenly started to look really realistic, at least much better. This was called an eddy resolving model. I mean, later on people said, well, now it's eddy permitting, or we need higher resolution. But it was really the first step, a big step forward. And it allowed to start looking into the full circulation. It allowed to abandon all these approximations. Geostrophy didn't matter anymore. Bottom slopes didn't matter anymore. We could really be able to do top to bottom circulation simulations, including the barotropic part and everything. And really it opened the door for many, many new things, new standards from which we benefit still, and which we actually carry forward still. And we had here this meeting the last 4 days, and some of the discussions I take home, well, let's start over again in the sense of look at the parameterization and so forth, but it really carries forward what that started. And so these were the flow fields. The first time that we had the transports that we can use to compute eddy transport that Anne-Marie was just talking about, the full transport in different levels. This actually It's a paper going back in I think it was Frank Bryan, Klaus Böning, Bill Holland, 95. We always think this is old history. 95, it's not that long ago. When all this happened. And so the circulations, the bottom layer came out suddenly with different boundary currents, and a lot of that started. So further development followed, improvement of the parameterization, subscript processes. So we had heard about GM already here today, NCAR, mixed layer dynamics, KPP came in, Bill talked about it, NCAR. Improved bottom topography, bottom layer representation, many things that followed later on, not all here, but from this step towards the primitive equations. And of course, at the same time, there was WOS, there was a modeling move forward, bigger computers that suddenly allowed this, but also new technologies. And one of these was the altimetry came along that finally allowed, or in fact, the CME results suddenly actually allowed to compare with observations, because the realism started to be there, and the observers, the so-called observers, started to get interest. And one of these new observations, of course, was altimetry with Topex coming along, that allowed to also do these comparisons. But on the other hand, people realized we need higher resolution. And so there was really an evolution in higher resolution, going from 1/3 to 1/4. Bert-Sempner, Chervin, 1/4 degree global. That was actually really a community effort, results that were out there being analyzed for a long time. POP came afterwards, 1/6 degree, Los Alamos, using the big atomic bomb computers out and using it for ocean circulation. 1/6 was enormous. I mean, people got dizzy from that number. And then with Frank involved, 1/10 degree Atlantic, again Atlantic, to see if we can get the northwest corner right. And so suddenly it was right, but afterwards I heard from Frank, well, we don't know why, and it didn't really happen in the next run. But it really allowed to get more and more realism, and this is a figure, it's a 1/6 POP result, where Li Fu then started to compare with altimetry. The eddy field was compared, the results were compared. But it's also allowed really a lot of computations, analyses that we were not able to do before. The meteor overturning in circulation Atlantic, with the depths in the vertical, in the top panel, with temperature in the lower panel, kind of how the temperature is changing along the files. You see wintertime mixed layer depths and the temperature of the mixed layer depths, the water mass formation, all these things we were able to start to do. Not final, but to start to do and look into this. And maybe bottom line here, there are many F.O. Bryans involved in all these papers that came out, of course, from CME, but also otherwise. And this is just work that was done by Frank, papers that came out of NCAR and otherwise with Frank involved, Peter involved, and other people involved. And I just list here the titles, and I'm pretty sure people will come back to this. For instance, the mean transport, maybe not so much the straight passage, but the actual angular momentum balance of the global ocean circulation, climate-driven polar motions that came along, methods of inferring changes of the deep ocean currents from satellite measurements of time variable gravity. And then Frank's work, for instance, on salinity and how this is being simulated in ocean models. What you see here is, in fact, one of the pictures out of this, where you see sea level and you see sea surface salinity. This is actually the North Brazil current. It's a kind of the north coast of the Brazil continent, where from the Amazon, which is sort of, you see it from salinity more on the right, the impact of Amazon outflow, freshening or otherwise, but you start to see actually in sea level these eddies moving along the coast westwards, and salinity actually has the same imprint. In temperature, you wouldn't see it. And it's one of these examples where you really see the impact, the dynamical impact of salinity, which in the past people always assumed the temperature is determining density. Salinity doesn't matter. It's not changing at all. And so this came actually in as a dynamical parameter that starts to become very important, and now we do have the salinity measurements. We do understand that salinity is very important. Frank was doing a great work also on kind of cage studies in, I think, Atlantic, also Pacific, looking at the diffusivity carrying salinity into basin boxes and so forth. So this all came kind of as a downstream ripples from the CME result that started at the beginning. And so with all this development, we now really have models on regional global scale that start to have great realism that we use now for many aspects to simulate the ocean circulation, simulate the coupled simulation, the climate simulation. We use it now for many applications. At the same time, we moved the observing system forward. Bill already talked about the observing system, some parts. I showed you a picture from altimetry. And we have to realize that both parts evolved. In fact, the communities came together. And I think CME was really essential to bring these communities together. When I was in the early WOS meetings with Bill leading the WOS meetings, there was always these observers and then the modelers, and these were completely different communities, and the one didn't like the other one. And I think we are now one community. We work together, and we have to do so. And we assimilate now. We bring observations and models together to get even better result and to use it for predictions. And NCAR, again, CMIP, for instance, the coupled model intercomparison project. The name is probably not really what it should be now anymore after all these years. But really, we moved into coupled systems. We moved forward. We deliver now something through the development that I believe actually started through CME. And that's also the standard. So how we do this, carrying this forward into the entire system. And just to demonstrate or show you one thing, the evolution of observations together with the model evolution, the model development. What you see here is altimetry. It starts in the upper left panel with CSAT. That was I think the 80s. The first satellite that was measuring that just for some time. What you see is sea level variability or sea level anomalies. And then came along GeoSat. That actually was kind of in the 80s where people thought, wow, great progress. And then we actually had TOPEX Poseidon coming up. You basically see the details now starting to emerge that were really so important to also test the models that developed, bring these together. And finally, you see here the very latest result from SPOT. Really the details now that come out. At the same time, of course, the models developed. The computers became bigger. And what you see here is the global 1 kilometer run, a coupled run, atmosphere ocean coupled run. You see 2 names down there, but the JPL guys, Dimitri in particular, Menemelis, were very heavily involved. And these are the details we can now simulate. And you have to reflect this or confront this with the SWOT results there. I would almost opt, the model is almost better, at least in its detail, but there's so much in that we have to look at now. 1 minute, yes, and I'm almost done. But we have also to realize that through altimetry, we are so used to just compare the surface parameters. Everything is surface, and I think we have started to limit ourselves, and we need to broaden this now. We actually need to broaden the trust in the models, the usage of the models. And in this 1 minute that's left, I will rush here very briefly through a work that, in fact, I started with Frank while I was here on sabbatical, using the tensor degree NCAR model to really look again in the eddy kinetic energy in this case, top 1,000 meters, 1,000 to 300 meters, and top to bottom and so forth, where you really start to see that's what we usually compare with altimetry. But we have to realize that if you go down, you see big bottom topography impacts, big really shifts to the western side of the kinetic energy. And my favorite part is really zooming in where this is the Indian Ocean, where you see really all the topography. You have a western boundary. Everywhere you have topography. You see the topography where the energy really filters through. It's enormous. And what's really important now is to split the kinetic energy up. And this is longer than a year. This is 6 months to a year. 3 months, 6 months to 12 months, 3 months to 6 months, where you go to shorter and shorter time scales, the energy goes up, 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 up. The structures change. Any time scale has its own spatial structure. And the thing is that the energy goes up, 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 and I think it's actually an underestimate on below 5 days because the forcing is not high frequency enough. And that means really we can use models to really study the full column of a kinetic energy. We can actually use the models to study how we need to drive the models and how maybe even how we need to observe the ocean, because satellites cannot give us this high frequency. So we have to come in through the models. If it's wind work or whatever we want to do, we need to, and we can use now the models. My last slide, Gökhan, last but one. We need to look forward. If we would have a Frank Bryan 2.0, kind of the next 30 years of a career, we are now at a point in history where we know this. The Earth is changing. Climate change, climate science is changing, and we are really asked now to deliver information, deliver advice. The modeling in the ocean, in the coupled system really has to change. And it's really more like simulating solutions, simulating what-if questions, answers. And this figure shows you, it's a 600-meter resolution icon, and I'm pretty sure you have seen icon before. It's in the Southern Ocean, that's Agulhas, the temperature, and in this case, chlorophyll. And it shows you where we are with the models. We can use them now to answer what-if questions, to carbon dioxide removal, to really look into what happens if we do this or that, and you have to extrapolate to the entire climate system. I don't have the time, and Gökhan is pushing me to finish, but my last slide, I think last 30 years, NCAR really made a big contribution, and Frank too. There's probably no need to answer a question.
Well,
It wasn't meant to be.
Yeah, Frank has something, so thank you, Detlef. That was great.
Yeah, I'd just like to add that, that early WOS modeling time, certainly BERT's calculations were, a very important part of that time. But also one that hasn't been mentioned is the FRAM effort in the UK led by Peter Kilworth.
True.
There was a tremendous amount of cross-fertilization internationally across these groups who were doing these first primitive equation, eddy permitting calculations.
Yeah. FRAM was limited to the Southern Ocean though, right?
Okay, thank you. So we'll take a break until 11. There are some snacks out there, so please come back at 11. And then we'll take a group picture right before lunch at 12:20 or so, I think. Thank you.
Okay, it's now 11 a.m. Let's go to the second part of the morning session. And our next speaker is Stephen Griffiths from NOAA GFGL and Princeton University. And the talk is Some History on OMIP and the Clivar Ocean Model Group panel.
All right, so thank you. It's really an honor to be here. I feel like every time I come to NCAR, this is like my second home in many ways. I could have given probably half a dozen presentations about the relationship between NCAR and GFDL because there's been so many over the history. Just on my little post-it here, just some of the history that we saw earlier. If you go a little bit further back than what was presented here, you would realize that Bill Holland was at GFDL before he came here. Bert Sempner was a PhD student in Princeton before he came here. So was Frank Bryan. Gustavo was a postdoc at GFDL. I'm sure I'm missing names. There's lots of others. The relationship goes way back. And actually, we've had a lot of visitors from Princeton here. And we've had some even move from Princeton directorship to the staff at NCAR, Jerry Mallman. It's been a long relationship. I would call it a friendly rivalry. And it's been a great relationship. I would say that these are the two labs in the country that do serious climate modeling. There's others that are up and coming, and I think it's a circle that is growing for good reason because it's an important problem. From the modeling side, there's the Brian Cox model, which is the beginning of the CME, the code that was used in FRAM, the code that then became MOM, which then became POP, which is now going back to MOM at CESM, MOM 6. So it's a genuine honor and privilege to be part of that relationship and part of that history. And the relationship that I played a role in a lot with people like Gökhan, Bill, and Steve Yeager, and a handful of other people at NCAR, is in developing what we call OMIP, Ocean Model Intercomparison Project. And the title slide here has 3 images of the AMOC time series. The one from a paper from 2009, which is the original core paper, and the one from 2014 from Danabasaglu, and the one from 2020 from Sugino. And it's just a bit of the history of the AMOC in these simulations. So if we go way back, not really too far back for a lot of us that were here, there was a meeting here in '98, a WOS modeling workshop, and there was a report. And you definitely don't need to read everything. And the thing that came out of this report was the word OMIP. There was a lot of people, you saw the nice presentation from Detloff about modeling and the relationship with WOS and CME. And the community was looking for global modeling, and groups were starting up. And how do you know what you're doing and how you share and cross-fertilize? And so the Model Intercomparison Project, the Atmosphere Model Intercomparison Project, had been around for a bit. And so the next thing was, well, why not? Well, OMIP, let's do it. Well, it was kind of, as Frank said in an email to me recently, it was a bit ambivalent, the relationship or the recommendation from the SSG at the time. But nonetheless, out of WOS came the Working Group for Ocean Model Development, a Clivar panel, which was tasked with, one of the tasks was to look at models and to intercompare the simulations. So this is the first group. We met after a MICOM meeting in 2000, early 2000. Chazaneh, Hasumi, Hurst, Burning, Gerdes. I don't remember, he was an admin person from WCRP. Pierce, okay. Griffiths, Tregier, David Webb. Much younger then and much more beautiful, but nonetheless, we're still handsome as we could be. It was, Frank was part of the first group, but I don't remember why he wasn't there. Do you? Oh, goodness. So anyway, you were there in spirit, and you were there at many of the subsequent workshops that we had. This group has continued, and it is an amazing group. So the first thing that we decided to do as a panel was to write a review paper, because at the time there was no compendium, no sort of place to go to teach people about models. There was no book. It was just basically handed down. A lot of it came from Frank Bryan and his disciples. And so we wrote a review paper that's still, I think, still useful. It's still read by lots of students. And it's, big paper, 70 pages, but it sort of laid out the baseline for what's going on with models in the community. And this figure is still used by Eric Chazanet in his talks. This sort of vertical, this was state of the art graphics 25 years ago. The Germans jumped the gun in some ways. They defined OMIP, a group out of MPI and Bremerhaven, said, let's compare our models in a common forcing, and a guy named Frank Rosk developed a data set based on ERA at the time. It was provocative, and they wrote a report, and they brought that to the first meeting of us in Miami, and we talked a lot about it. And we debated whether we should, one of the debates was whether we should call it OMIP. It seemed like a pretentious term because we don't know how to run climate models without an atmosphere at the time. How do you do the boundary conditions? We're still debating those questions. We met in Santa Fe next. I think Anne-Marie was on sabbatical there with Rick Smith. And we had, there's Frank in there at a fantastic little hotel right off the square. And it was just us. We had a few visitors all the way from Australia. We had Trevor McDougall, who seems to turn up at a lot of these meetings that are in these fine places. Gervin Madoc was there, and a handful of others that sort of was a tradition of these meetings. We had people that were central and people that were on the panel, and friends that just wanted to show up. So we started talking about diagnostics and what do we do? How do we develop these simulations? And we really didn't know what we were doing, how hard it was going to be to develop the protocol for an experimental protocol for model development in a comparison. And this was then a year later in Hamburg with some of the same characters and a few extra people. There's Reiner up there in the top corner. Larry Gates was there. And the thing that you might know, Larry Gates was the originator of the AMIP project. And he said, just do it. He just said, just call it OMIP and do it. Don't just analysis paralysis, just go ahead and do it. Well, I would say that we basically ignored that advice and continued to ponder the questions for the next, it took about a decade. There was no consensus on the forcing data set, though many problems were found in the German OMIP. We were largely at an impasse, no consensus on the bulk formula. Some people said it wouldn't matter, some people said it would, and so we had to go off and do some tests. It's like, one group should use this bulk formula and the other ones. Well, we decided we needed to use the same bulk formula, and a year later, I think, we decided to use the NCAR bulk formula from Large and Jaeger. This was in combination with the Atlantic panel in France, a meeting we had. I think there's Detloff in the front somewhere with Bill showing up somewhere in there. And Bill came to this meeting really, really clearly disappointed with the German data set. He said, we can do better. I can do better, basically. And I think he did. And that was the leadership of the NCAR effort to make OMIP or core, which it became, realized. So the consensus really became around the efforts of Bill Large and NCAR with Steve Yeager to develop the core forcing data set. So a year later in Princeton, notably with Alistair and Sonia with their two kids in the front, which is really a classic picture of the family relationship we have. Everybody can just bring anybody to the party. It was great. There's Matthew Hecht there. This was a really wonderful workshop. It was, I think at the time, CMIP 3 or CMIP whatever. Actually, it was CMIP 3, a climate model workshop. Brought a lot of people to the table, as well as the WGMD discussing OMIP and CORE. This was the meeting where we decided to call it CORE, Coordinated Ocean Ice Reference Experiments. The ice is not part of the acronym. And my recollection is that was Frank Bryan. He recollects that it was Kelvin Richards, and so it was probably a bit of both who thought of that name, and it stuck. And it was it's been quite a success. We've run about 500 years, 100 years to allow equilibration, rather than 100 years. We decided not to reach out to PCMDI. We just decided to be humble and just keep this project at the grassroots. And in many ways, OMIP today is kind of still a grassroots effort, even though it's part of CMIP. And let me keep going. We went to Hobart next and had a Southern Ocean workshop attached to the working group panel meeting. There's Marika, who took over from Frank on the panel. And who else is there? There's Anne-Marie, myself. Wonderful workshop on Southern Ocean. So what did we do? At the time, we had results from 5 or 6 other groups are still struggling. So we're still struggling. The problem was a lot of the groups didn't have the model configurations. They didn't have an ice-ocean coupled model at the time. They were still building their ice-ocean coupled models. And to run these models and to develop the forcing took a while. And so that's why it took so long to do this. It wasn't like it was a couple of weeks or a couple of months to do this. So to this day, there remain unsatisfying methods for the salinity forcing question. We talked about this yesterday and the day before in the panel about a potentially new method instead of the salinity restoring that we do with these ocean forced simulations. But we only had 3 simulations at that point in Hobart and no isopycnal model yet or hybrid coordinate models. They were still building the technology at their groups. But then we went to Bergen, and 2 years later at a numerical methods workshop, similar kind of to the Commodore workshop that the panel helped organize this week here in the Bergen Harbor, just a fantastic spot. And there's the panel, and at this point we see Gökhan join, because Marika had to move on and she had other things to do, and Gökhan started joining the panel. But at this point we had, I think, a critical mass of model groups that we decided we have enough. We had a geopotential model, 4 geopotential models, 2 isopycnal models. I'm pointing up and it's not following my hand. And 1 hybrid model. So we declared that we had enough to do what we would call a paper. So we started writing a paper, and it took us another 2 years to develop that paper. Originally targeted in ocean sciences, but we ended up going to ocean modeling. Future work at NCAR, everybody started focusing after this core normal year forcing effort, which took 9 years. We decided to work on the interannual forcing protocol and running the models. Sidebar, Burning, Tregier, and Gerdes were emeritus. This panel is notorious for its emeriti who just love to go to the meetings and continue to do the work because it's a good group and we do fun stuff. And so it's actually been politically a difficult situation with the SSG, but we still do it. Next meeting was at the Hadley Center, and this is notable for the workshop we organized, 30 years of Jet McWilliams. Well, 2009 was almost 30 years, but I can bet you they started writing the paper in 1989 is my guess. So that was a wonderful big workshop. A lot of people turned up for this eddy parameterization focused workshop in celebration of Genta McWilliams' pivotal piece of work. So we finally had a paper. This paper, Griffiths et al., 2009. We talked about the difficulties in that paper, one of which is the North Atlantic salt advective feedback problem and mixed boundary condition problem with salinity restoring, and the difficulties of defining a common salinity restoring across all groups. We never did, and we're still arguing about it. Large and Jaeger published their 2009 core interannual forcing data set in climate dynamics that year. And so we set plans for doing analysis of the interannually forced simulations. A lot more people were interested in the interannually forced than the core normal year forced. So we got a good number of people to come on. Instead of, I think we had 7 for this paper up here, 7 groups. I think we picked up another 7, so roughly 15 or so in subsequent papers. So speed going through some of the panel meetings here. The next one was back in Boulder, a predictability workshop attached to the panel workshop, and I think it was in combination with a decadal prediction or DECSEN or decadal variability panel as well. And there's the panel meeting on the side, the group meeting. We went to Venice in 2012 and back to Hobart in 2013 and Kiel in 2014. Each of these workshops, we would come together and report on the interannually experiments that we're doing and look at the different places that the experts in the room wanted to analyze. Southern Ocean, we had 2 groups or 2 papers out of that, 3 or 4 papers out of the Atlantic, and two papers out of the Arctic, 1 out of the Indian. So it was just a really interesting time. We'd come and argue about the different analysis and update each other on the different results. And out of that work came 10 papers. And these are really still benchmark papers of the state of the science of modeling the real ocean of that era. And the last paper came out in 2020. So people were, until 4 years ago, writing papers about this CMIP-3, CMIP-5 class models. You're running with the core interannually forced. So the workshops on ocean forcing came about in Grenoble in 2015 because for various reasons, core stopped in 2009. And I think it's largely because it was just hard to get the data from NASA. And Bill just became probably exhausted. So we had a workshop there, and the Japanese raised their hand and said, JRA, we will do it. And that was a great relationship with Sugino, helping to build the JRA 55DO with lots of input from Lars and Jaeger. And so that led to the real first time we called it OMIP. And so we wrote a paper in 2016 with the protocol and the diagnostics, which is still a big paper for CMIP, ocean diagnostics, and we had a paper on the biogeochemical protocols for OMIP. CMIP 7 and afterwards, what's going on today? Well, there's a couple of ideas out there. A lot of people are unhappy with the way we recycle the interannually forcing, going from 58 to 2020 and then going back to the beginning. So one of the ideas is to have a repeat year to spin up the models and then do the interannually after that. There's another potential idea for doing the surface restoring of salinity instead of doing the restoring, something different, which is still in the works. So should OMIP be part of the deck? That was a discussion that I had with John Dunn, who's co-head of CMIP, and we decided not to, but it is still part of CMIP. This panel, now it's called the Ocean Model Development Panel. It changed names in 2014. It's got a pretty big impact. It's got an H score on Google of about 44, which is not bad for a panel. And I just want to close with a thank you to NCAR for the time I've spent here. I spent 2012, the summer, with my family. This is the road from Durango to Silverton. This is one of the 12,000-foot peaks in the Rockies. I took a hike with Enrique Kirchester and his family. They spent a lot of time here as well. Frank Bryan and the NCAR Ocean section has been just the leadership and vision throughout the process of developing OMIP and other things. CME we heard about. Visiting NCAR, everybody should do it more than just the week or few days you're doing it now. You should come back, bother them enough to give you an office, and it's just a great place to be. I'm deeply appreciative of the kindness and wisdom shared by the friends for 31 years of my career. 50 years of oceanography is not a long time. From some perspectives, it's a long time from others' perspectives. We need more. We need to keep the passion, the vision of this science that has come from this division and NCAR in particular, blossoming and continue to bring the young, smart people in the field. We really need it. I mean, the planet's changing. We need to understand the science. It's an interesting problem, even if it wasn't global warming going on. Climate science is a very interesting problem, intellectually challenging. So, thank you.
We have a few minutes for questions.
Thanks, Steve. For this core looping problem, would it be possible to, generate random variability on interannual timescales and kind of stochastically generate a core type forcing?
That's kind of what Bill Large did with the core normal year. He generated some synthetic synoptic variability and put it together and called it the normal year. So yeah, you could do that. You could do something like what Bill did. You could do that. One of the best ideas that I have is to just do the first 10 years and loop that in the early part of before we get a huge signal of global warming, to do just the first 10 years, spin up for maybe 50 years of that, or first 5 years even, and get the interannual variability of those few years. And that's a pretty simple thing. You don't have to do too much to do that.
Thanks, Steve. So I'm not familiar with what your alternative to restoring for salinity is. Can you just say something briefly about that?
Yeah, it's effectively not using a land model, but thinking like having a land model. So you adjust the salinity, the freshwater transport at 40 north and 40 south to be close to CMIP ensemble mean, which is a balanced models. Don't use reanalysis because they're not balanced. And We've done it at GFDL, and we were able to run without restoring with this particular approach, and there's a lot more testing that's still being done. Alistair is promoting it, and it comes from a paper from Matt Harrison et al. In 2022. It's in James, which is about as much as I can tell you at this point without going into further details.
I'll just add a little humor related to our the relationship of our centers. As when I was moving from GFDL to here, I can't remember exactly who told me, but he said there are 3 climate modeling centers in this country: Hertz, Avis, and Rennerec. GFDL was Hertz; they were the gold standards. NCAR was Avis because they tried hard. And I won't say who was Rennerec.
That's great.
Okay, let's thank Steve one more time. Our next talk is from Eric Chassinet from Florida State University. And Eric will talk about high-resolution modeling in the age of SWOT.
Thank you. Thank you.
So just for the record, I was an ESP postdoc between '88 and 1990. It was just an amazing time, very fertile ground, a lot of amazing postdocs, students, staff, where we were able to work from idealized QG configurations to CME configurations. So it was a time when the section really spent a lot of time looking at fundamentals in oceanography in addition to ocean modeling. So I just put this title up here so to allow me to ramble a little bit, or just give a few thoughts. I've been a big proponent, or at least I've really enjoyed keep pushing the limit of resolution in ocean models. Personally, I derive a lot of satisfaction from finding new, all the insights that one gained by increasing resolution. And I think in the context of SWOT that was mentioned by Detlef, there's a lot of things going on that we're discovering again. So here, I presented this week on the impact of properly resolving the bathymetry even at 1/50th a degree, and the one on the right, in order to get a proper Gulf Stream penetration as well as sea surface height activity. So I'd like to bring something up. It's more of an anecdote, but it's something that I'm currently working on, which is the Gulf of Mexico. And what you see here is a regional model. It's HICOM, but it doesn't really matter, I think, which model. But on the left is what we consider pretty high resolution at 1/25th degree, and then we did it also at 1 kilometer, 100th degree. And again, bathymetry matters. And what you see here is a very, downstreams of Cozumel, there is a seamount lake that rises all the way to 20 meters. And it is in the 1/25th degree bathymetry, but doesn't really have a strong impact on the circulation. So it's just interesting. First, we thought something is wrong because we didn't expect to see that. But then came SWOT. So just in the past few months, we started to look at the passes over the region. On the left is the traditional gridded sea surface height interpolated fields from Aviso. It's a 1/4 degree. And then the little arrows are the geostrophic velocity. On the right is the same, a pass on the, so it's in this case, September 6, 23, and you can start to see that the small features are represented in here. So there's a lot of information that pretty much every 2 to 3 weeks is coming and giving us that. So here, I just put a few snapshots. This is in April, so you can see again the little eddies that are generated down of Cozumel. So it meant, that feature. And here's another snapshot. So why do I bring this up, and why does it matter? This is working. Okay, so what you see on the left is a data assimilative 1/12 degree field. On the first, and they all, the two models on the right are the 4 kilometer and the 1 kilometer initialized from GOFs and ran for several years. And one thing I'd like to bring your attention a little bit is that all the little eddies that are generated here actually keep feeding on this cyclonic feature that separates the eddy, the loop current eddy from the proper loop current, and it keeps existing in here. After a few months, the 4 kilometer is not able to keep track of the, in quote, observation as represented by the data assimilative model. So you see here, this, what we surmise is just, it's just a casual observation. I'm just sharing with you thought process as we look at those simulations. Doesn't mean that it is truly exact. But we kept integrating this model for 3 years. And pretty much for 2 years, for some reason, the 1 kilometer is able to keep track of the data assimilative one. So you need to be aware that the boundary conditions are provided by this model here. This is a nonlinear system that doesn't make a lot of sense, but what we surmise is that the ability for the 1 kilometer to generate all those little cyclonic eddies on the western edge of the loop current do matter. At least it's some insight we're gaining. Maybe it's going to be a futile, not really going to pan out as being very useful, but it is a thing. Now going back to more thought, so I'm going back and forth between various topics. This week we heard a lot about the Gulf Stream separation being an issue and something that is still not resolved. I think Steve, Bob, many people mentioned that we don't have any, they're very sensitive to the numerics and the model that you choose. And I'd like to point out something, especially, Frank, I remember his frustration, and I think it's been shared many times. In his 2007 paper, Regional Atlantic worked pretty well, did the same thing with a global model and everything fell apart. So I'd like to bring something that was just happened a few weeks ago. It's a work that Alan Waldcraft is doing with MUM6 at 1/12 degree using comparing the Boussinesque and non-Boussinesque. And at some point, there was a, I'm sorry, I think Bob can probably expand a little bit on where the difference, but by using one single parameter different, you see the classic overshooting Gulf Stream on the left, and maybe it's a little southward separation using MUM6 by just changing one parameter. So many other factors are known. I think the one that we often surmise as being the biggest difference between a regional Atlantic and a global is the ability for a model to generate proper water masses for the deep western boundary current and how the deep western boundary current actually interacts with the Gulf Stream. The other one is the atmospheric current feedback. I already mentioned this in the case of the 1/50th degree work that we did, but this is a work that Renaud et al. Showed is that you see that when it's uncoupled, you start to see a lot of eddy kinetic energy, and the coupled or the ocean atmospheric feedback, which is an eddy killing effect, helps improve the pathway. So the interaction ocean atmosphere matters. And here is a work also that Alan Waldcraft did. On the top is HICOM, on the bottom is MUM6 when we're doing the comparison. And if you look on the left is absolute wind forcing, the same simulation done on the right, relative wind forcing. And in this case, the Agulhas current, the shedding of the Agulhas current rings, instead of being regular, becomes better represented and moving westward. The big difference that you see is that you actually end up killing all the eddy activity in the interior when you compare to the absolute wind forcing. So in practice, relative is a physical way to go. If you're using on the ocean, when you want to achieve the right variability, here is, so we need to address. So the main thing is that we want to be able to increase the level of eddy kinetic energy in your model in order to use relative wind / current feedbacks, which introduce about roughly a 30% reduction in eddy kinetic energy. So one can try to reduce the viscosity that you use in the model as you go relative, or what we're starting to play a little bit with, and that's just a few experiments that we did, you can start to look at higher order operator things. So what we did, going back in tradition of the models that we're doing at NCAR when I was here, using the 2-gyre configuration and going from 20 kilometers to 1 kilometer. And roughly, after 20-year integration, looking at the last 5 years, the mean circulation is about the same. And here is, on the other hand, the representation is quite different. I mean, as you go from 20 kilometers, where you do not really, maybe eddy permitting, 10 kilometer, the traditional 1/10 of a degree, and then going all the way to 1 kilometer, you see a lot of sub-mesoscale features dominating the circulation. You don't even see the western boundary current or the, but the main point is that if you look at the kinetic energy, the time evolution of the kinetic energy over the domain, is that, so all those experiments are done with a barharmonic. There's no difference. So the dashed line is the fourth order, and the solid line is the second order. But roughly, as you start to go from 10 kilometers, you start to see a jump in the available kinetic energy, and then you roughly double each time as going from a second order to a fourth order. So as you increase resolution, the fourth order scheme appears to play a bigger role. So how does this translate into North Atlantic HICOM configuration? I'm just going to focus on the those two plots at the bottom. This is, they're using our traditional combination of Laplacian and barharmonic that we have found work best in our system. So you do have an increase in overall kinetic energy when you use a fourth order, but mostly I just want to point out a little bit of a surprising results which we haven't fully exploited, or so I'm just, showing to you what we end up with. But this is a traditional HICOM 1/12 of a degree, about 6 kilometer resolution, where you have a separation at the cape, but a very diffuse interior, a jet that is not coherent, that doesn't penetrate into the interior. Just switching to the fourth order, you start to see a picture that is better penetration, more coherent, and maybe a little more, in quote, inertial. Jet, that's the way I like to think of the Gulf Stream as being a little more, and maybe a little more inverse energy cascade from the small scale to large scale as well. And on the right is a traditional Aviso mean sea surface height. So you start to see a pretty good agreement between the two. We haven't looked at those simulation in detail, so these are just preliminary results. So same thing. If you look at the sea surface height variability and compared to observations, there's a big jump. You see a lot of eddy activity prior to the New England seamount, but it's a much better distribution once you go with a fourth order scheme. If you look at the mean flow, so one of the things that we are a bit puzzling is that the slope water ingress is much larger in the simulation than in the observation. So it has an interesting, I would say, feature in it that we don't fully understand where it's coming from. So, and that's, you see it when you look at the mean velocity, you see this kind of a second branch here at the top of velocity of flow coming from the slope current that does not appear in what we know of the observation, at least. So it's overly too strong. But then, we usually traditionally have not looked a lot at the SSD, but the SSD bias is something that's been mentioned a few times. And in this particular case, it does seem to improve the distribution. So in summary, just a few remarks. Just there's a strong impact of the mesoscale, submesoscale on the large scale. This week we talked a lot about, can this be parameterized, or do we need to actually have higher resolution to have all those effects truly taken into account? Large scale circulation and water mass transformation are very sensitive to proper representation of bathymetry. So how can we include in coarser resolution models better include the effect of refined bathymetry into it? And then higher order advection schema, just one example, seems to be promising. That needs to be further investigated in detail. So, thank you.
Thank you, Eric. We have time for a few questions.
Thanks, Eric. Very nice talk. I'm wondering, do you consider trying the upwind scheme for instead of a centered scheme?
I don't have the answer. Maybe if Bob or anybody was more, Alan would be.
We've talked about that in the context of, for instance, the anticipated vorticity scheme. The tricky thing, the way that the vorticity advection is formulated, it's rolled together with the Coriolis scheme. And Coriolis, you have waves going in multiple different directions. So the sense of streaming for the linear terms is not obvious. If you separated the linear terms from the nonlinear terms, that may open up the prospect of using a higher order upwind biased. You obviously don't want to go to simple first order upwind, but a higher order streaming sort of scheme might be a very interesting thing to explore.
Bob, may I ask you also maybe if you can expand a little bit on the difference between Alan's simulation with this parameter? How does it affect the solution?
Yeah, so we don't understand why. The specific thing that we're doing there is some of the other terms we have an upwind biased continuity solver, again, exactly like we were describing for momentum, and you have to do that for positive definiteness, and HICOM has done that forever. In some of the other terms, if you took a second order centered estimate of the thicknesses used in the horizontal viscosity, and you replace them with the implied thickness from the continuity solver, that's what that difference is. We don't understand why it should be that big, but there you go. There are plenty of things still to be explored in the numerics of this model, and I'm sure many others.
Any other questions? If not, let's thank Eric one more time. Our next speaker is Deepak Cherian. Deepak is former NCAR and now working at Earth Mover. And Deepak will talk about, that was a great title, property tests for ocean models, how to specify it.
Can you hear me? Yeah, so thank you, Gustavo, and all the organizers for giving me this opportunity to speak. As Gustavo mentioned, today I work for a company called Earth Mover with Ryan Abernathy, who most of you know, I bet. And I spent a lot of time thinking about data and software infrastructure, so it was a good excuse to come back to thinking about ocean physics. Before I joined Earthmover, I was at NCAR and I had the really good fortune to work with Frank. Frank was my collaborator, supervisor, and mentor for 2.5 years and more. And I really enjoyed it. It was really a high point of the last 5 years. And I spent some time trying to think about why. And the one thing that stuck out to me was that I would go into Frank's office, and we would talk about the things that I was working on, he was working on, all of this. And very frequently, I would go back and then find something to look up. And this had nothing to do with my research, right? And so, like, for one clear example I remember, I walked in probably talking about mixing and models and observations, yada yada, and Frank would talk about simulations of mantle helium. Like, how many offices can you walk into and talk about mantle helium, right? And then I remember coming out and then reading Stommel's beta plume paper again, just because all those ideas would come up. And as a young scientist, I've realized that is a really rare and valuable experience, just the ability to get exposed to new ideas, and Frank was very, very good at that. And it is hard to say thank you for such a contribution. So I'm going to try and do the hard thing, which is I'm going to try and inject some ideas into Frank for his retirement so that he stays engaged. And I'm going to approach this, to keep it interesting, to approach this from a software engineering perspective and talk about what's called property testing, how you might think about this for ocean models, and I'm going to ask, can we specify it? And this is a reference that I will point out later. Super short introduction. There are things called unit tests. So you write some code. How do you know that's correct? You write a test. And general, you approach testing. I define an input. I define an expected output. I assert these two are equal, and you do that till you get bored, right? Or you find a bug, you fix it, you add something else. A super simple example for sorting a list. Let's assume that the input list has 3 integers, 3, 2, and 1, and you want to sort it. So you assert that the output is 1, 2, 3. Awesome. And then you can write another one. 30, 1, 2, 3 sorts to 1, 2, 3, 30. Great. So, it's OK. There's a better way to do this. It's called property-based testing. It's about 30 years old now. I think the first paper is in 1999. And they frame the problem very differently. You define the input space. You define properties of the output after you run your code. And then you assert those properties are satisfied for inputs that are kind of pseudo-randomly satisfied from the input space. And if you're not satisfied, you found a bug, you try to shrink these examples to find minimal test cases, right? So that's a lot of words. Let's just look at the simple example of sorting a list. This is some Python code. It uses a project called Hypothesis, which is quite good. But should be fairly easy and readable. Here's a function called sort. It takes a list of integers. It returns a list of integers. Sorting in Python is built in, so it's really just very simple. Down here is my test case. It says, give me a thing, probably unsorted, sort that. And then I'm going to slide through the list of integers and assert that the first element is less than the second element, right? So that is the definition of a sorted list. The trick is here. What cases do I test? So I'm using Hypothesis, and this is saying, hey, generate arbitrary lists of integers of at least size 1. That's all you tell it. And it's going to just pseudo-randomly generate a whole bunch of integers and cases and run it through your test program. This turns out to always be correct. So here are some statistics. It ran 100 passing examples in 0.4 seconds, right? So I didn't hard code the input. I didn't hard code the output. I just hard coded the property of sortedness. And I say my function has to do this, right? This works. So let's see what happens when it fails, right? So I'm going to write, this is a bad sort. I'm going to sort it, and then I'm going to swap the first and last elements, right? And so this is only going to work for a 1-element list when the first and last element is the same. It's also going to work for a list of constants. And so if you try this, you'll see here's the output from it trying to run these test cases. It puts in negative 20,007 for some reason. That one succeeds. It tries 0 to 1 and says, hey, that's failed because this is a bad sort. Then it tries 1, 0. It says, that failed. It does a bunch more. It tries this very, very long list. That fails too. Eventually, it comes back to 0, 1 and say, OK, that's still failing. I'm going to try 0. That's failed. Let me try 0, 1 again. Still failing. I'm going to try 1. I'm going to try 0, 0. Both of those have succeeded. And I'm going to end with saying, hey, the smallest example I could find was the list 0, 1. And this has failed, right? So this illustrates this idea of both random sampling as well as shrinking. the thing shrunk towards lists of smaller sizes. Like it's found the 2-element list, which is the smallest example. It's also found that it's also made the integers shrink towards 0, right? So the falsifying example is 0 and 1, not 1,000 and 1,001, which have also failed, right? So this is kind of why it's powerful. It's like once you write the property down, it will try and find you minimal examples that fail, right? It comes from these languages such as Haskell and Erlang, which are these languages kind of blur the boundary between abstract math and computing. But it was kind of pioneered in Haskell for this thing called quick check. And a lot of this, my title, for example, really is inspired by this talk that I watched. It's totally worth watching. It's only 45 minutes by John Hughes, who's a computer science professor and part of the group that really put this idea forward. This title is called How to Specify It and is a guide to writing property tests. And how do you think about it, right? And so we have ocean models that are very complicated code bases. How would you write a property test for an ocean model, right? Why you want to do this? One reason is complexity. This is a little bug I found in NCAR's configuration of MOM6. These two profiles are the vertical profile of diffusivity in blue and viscosity in yellow at 0, 140. So in the tropical Pacific. The bug is this. The Prandtl numbers, the ratio of viscosity to diffusivity is wrong by, it's a factor of 200. This is wrong. It's very wrong. And it turns out to be this very subtle bug. I became very good friends with mom, set diffusivity F90 for a few days, then tracked it down. It was very, very hard to find. It was very subtle. It has implications for the EUC in these models. And we've known that the EUC was too weak in these models, but no one ever looked at this, right? I mean, these models are so complicated that even fairly simple misconfigurations can be hard to find unless someone looks at the right place. Here's Frank commenting on GitHub. Compare the bottom two plots. This is the seasonal cycle of the EUC, and once you fix this, this kind of matched my results. You fix a kind of 20% bias in the strength of the EUC, right? And this is one of the reasons was this bad misconfiguration. Second question also, I'm pretty sure we're about to see a flood of AI models of the ocean approaching us in the next few years, and it's all going to be great. But how do you ask it the question? What do you know about Rossby waves? What do you know about this and that? Right? A lot of this stuff is getting hidden, and how do we get confidence? So for the next 8 minutes or so, I'm going to talk about some ideas. There is no rigor here. I spend more time reading computer science papers than oceanography papers, but I'm sure these ideas have come up before. I'm happy to, I really like suggestions and what to look up. It's mostly describing my attempt to think through the problem and also, like I said, to keep Frank busy in retirement. Some prior art exists for this kind of thing. Alper has a very cool paper from 2018 where he uses a theorem prover to prove the bit of detail. Right? So KPP, the mixing scheme, divides the vertical water column into 3 parts. So the middle and the bottom part, so the surface boundary layer and the interior ocean, you have 2 different diffusivity profiles, and you can match them at the edge. And they found a bug where you were getting negative diffusivities, which should not happen, and was connected to this matching at that boundary. And so Alper, it's a very cool paper, you should read it, manages to put that into a theorem prover and proves that this solution was correct. No bugs, right? And you get confidence that this kind of thing is not going to happen, and it's not good. Debugging attempts that took several days are not necessary for that part of the code, right? MOM6 has very interesting tests that it calls novel tests. So one of these is the scaling thing where you run through and check for dimensional correctness, which is very cool. It's also got the rotational test. I guess you solve it this way, and then you rotate your domain 90 degrees and solve it that way, and you make sure, and you use this to look for bugs, right? And so these are kind of interesting, but there's also no dynamics. And so I'm going to come at this with a little different angle. I'm going to make a few assertions. For one, testing individual terms of the equations of motion are probably easy by some definition, and they have to be valuable. For example, if you wanted to test the advection scheme, you could stick in a little anomaly here in a doubly periodic domain, and then advect it in any random direction. As long as you advect the right number of time steps, you have to get back to the same place, right? This is a property test that you could write for any, for random configurations of that eddy, right? And random velocity fields, and you could just hit it. Another property test you could write is for arbitrary decompositions of this domain, non-uniform, to the extent that your framework allows, and make sure that you always get the same thing. You could assert that the mixing scheme must destroy variance and not have negative diffusivities, for example. And so given any kind of input that looks like this, you should get a smoother profile on the output, right? So these are properties that you could assert. I'm also going to assert that the shrinking stuff, how you come back to small and simpler inputs is probably doable. And I'm going to say that dynamical properties are hard to think about, and that's what I'll spend the rest of the time on. And like a lot of the challenge is going to be in creating test cases that are verifiable in a short period of time, right? You don't want to integrate your model for like tens of years to find a bug. And it's not going to work. And so for a simple example, let's assume I implemented geostrophic flow and I had this error in the sign. What properties would you assert about geostrophic flow to find that bug? Anyone want to volunteer? Yeah, good one. Nice.
Rotational symmetry.
Ooh, good one, good one. Yes, exactly. This is how you think about it. And you can see why this appeals to physicists, right? Like, so I got, yeah, non-divergence. You could also assert that the velocity vector and the pressure gradient are normal, right, with the right sign. And so these are properties that you can assert about geostrophic flow and find that bug. This is a great general exams question, by the way. Downside of this, in this particular case, implementing divergence is about as hard as implementing, the calculation here. So you're probably going to make the same mistake on both sides, but illustrates the point. So now we go to the hard problem. What are the properties of the ocean circulation? And I thought about this, and the first thing that came to mind was this image, right? It's like, oh yeah, things move westwards, or like east-west asymmetry. Such a cool property, except it's a little too easy, it seems. And also, things move westward for some definition of thing, and that definition of thing seems to change every 15 years. Like, we don't actually know what these things are. So, like, how much can you assert about this? And so, if you go and watch this talk, John Hughes actually goes through like 5 ways to think about properties. And so we're going to do that and try and adapt them to the ocean. So first question is that an invariant, right? And so an invariant would be if you sort a sorted list, you get the same list back. Right? It's already sorted. It's kind of an idempotent operation. And so at first, I wasn't very satisfied with this. You could assert that conservation principles are satisfied after n time steps of integration for any arbitrary initial condition, any arbitrary group, any arbitrary domain decomposition, right? This is actually, it seems pretty rigorous, but it also feels a little unsatisfying. But that's a good invariant. Here's another invariant. You could say that balanced flows remain balanced, right? And so simpler examples are geostrophic flows. If I insert a random geostrophically balanced anomaly, it has to stay balanced. You could do that for eddies. You could maybe go cyclostrophic flows. You could construct these analytical solutions. And then really, just 2 days ago, I realized you could stick in modons. So these are very strongly nonlinear solutions. Theoretical theorems exist, right, for these things. And we think that Chris Hughes has a paper saying that, oh, maybe we see these in the real ocean, right? And so that's a modon in a moving frame from SSH. And so you could do this for like arbitrary modons and arbitrary flows and arbitrary grids. And maybe that's pretty useful. So that's a little more interesting to me. A second thing that John Hughes mentions is you can ask what is the post condition. So this is where you make a change to the input and you assert something about the output. So going back to my sorted list example, I could stick the minimum possible integer for your computer platform in there. It always has to be the first element of the output, right? So I've made a known transformation, and I can assert something about the output. This one was kind of hard, but I think like one way to do this would be to use a dispersion relation, right? And so those tell you resonant frequencies of your system. So if you set your system up, and you forced at those frequencies, so you pick a random point on the dispersion relationship, and you force the model at that, you have to see a resonant response, right? And so you add this thing to the model, and you expect to get something back at that frequency. And if you're off it, you should probably get nothing. So this also seems very promising to me, but then some frequencies are really slow. Again, you don't want to do decadal frequency waves, right? It's going to take way too long, but maybe you can configure the model so that that's actually a decent amount of hold time. The first post condition that I actually thought of was geostrophic adjustment. Right, you stick in a random anomaly on the SSH field, it's going to adjust, radiate a bunch, but the problem is that it's going to radiate a bunch of transients. And then waiting for transients to die out is a really long time. And so this, to me, was where I started to get stuck, right? Like the core problem about a lot of this is if you stick in an unbalanced anomaly, it's going to excite a transient. and you know, a lot of our theories are about equilibrium. And like it seems to me, at least from what I remember, very little about transients, right? And so if you need to assert properties about the transients, it feels like to really make like big progress here. So yeah, you could think about something like this, or maybe, you know, here's one way to think about a transient. Let's say I forced, this is a rotating planet, so I force some wind stress at the eastern boundary. I'm an observer staying here, and I say, assuming barotropic flow, I see the first signal in like order square root of GH, right? This wave's gonna come by. I'm gonna see the signal after n amount of time. And you could do something perhaps similar with kind of adjustment to Rossby waves. So that's the phase speed of planetary scale Rossby waves on a rotating planet. And so you can assert properties about this maybe. I'm running out of time, so I'm going to skip. A second kind of very rich set of ways to do this is to think about metamorphic properties. So this is where you do related inputs, give you related outputs. And so one way to do that would be taking my wave example. I run this for h, and I get, you know, I see a signal here after a certain amount of time. I can now run it with 4h, and then I should see my signal there in like half the time, right? And so you assert the relation between the two, and you get rid of the order 1 constants, right? And so you can do a bunch of rich things this way. And again, but this still comes back to this property of transience, you know, but metamorphic properties remind me about non-dimensionalization. Like if you had one non-dimensional parameter, that already tells you which two solutions are related, right? As long as you change your dimensional parameters to keep that non-dimensional parameter constant, the solutions must be similar. But again, this is again a very like equilibrium thing, like, and I at least am not aware of how you would do that for transients. I'm going to skip that too. And so I asked, can we specify it? For a while, I wasn't sure. Now I think it's possible, but it's hard. Lots of the things that I ran through very quickly are linear, except for modons. Modons are very strongly nonlinear and seem very powerful. Can we make small examples for rapid testing? That seems very hard to me. We need to assert properties about transients and very hard. But we should try it, I think, because it's fun. It's really great teaching and learning tool. A lot of these computer science papers, they always end on, here's a test problem, here's which properties were effective at finding them. It's a very empirical thing of this is useful, this is not useful, and like it feels like we need to do that exercise here too. And I'll end on, I mean, it struck me 2 days ago, a lot of the core challenge was really identified a long time ago, right? Like when Stommel asked, why do our ideas about the ocean circulation have such a dreamlike quality? And like all of our models seem to be heading towards more of the really pretty nightmare territory, right? It's like putting them together, very hard. Anyway, thank you.
We have time for questions for Deepak. Alistair wants to ask, but he's shy.
I think it's fabulous that this is great stuff. I mean, I think this is exactly what we need in our GCMs. I think one thing which I like the idea of testing with small tests is good, but even just building a small test is very expensive in terms of human resources. Just trying to configure a GCM to do a small thing is hard work. I'd just like to ask you though about one of the issues about the kind of property testing at the function level. Good, but the interactions between functions can be hard. And an example would be reverse and sort. The sorted reverse list will be sorted, but the reverse sort listed would be the reverse sort. And just testing those interactions at the kind of level of subroutines for a GCM can be really hard. And we had a conversation in the last 4 days about just the order of algorithms, and there are people who think we should do things one way and other ways and so on. So that's testing a GCM. It's 250,000 lines of code. It's a tough problem, but I think it's great that people are thinking about this.
Thanks. Yeah, I think that's why when I try to approach it from the physics and dynamics point of view, it's more like an integration test. Right? You're testing the whole thing together at one go. And fingers crossed you have enough terms. One point I wasn't very clear about is like part of the idea is to test multiple terms together, right? So once you hit balanced flows, you have at least 2. And that's very useful, I think.
Spencer?
Albert has a question.
Spencer has one.
Oh, Spencer has?
So yeah, really nice talk. I particularly am interested in the idea that we can use this to try to push machine learning models of the ocean to be more physical, which is the thing that I am frustrated about when I read some of these. I mean, to be fair, they've only been doing it for a very short period of time, but yeah, often I'm just like, what? This definitely is not physics. So I feel like, have you had thoughts about, so a lot of this transient stuff, if you're running like a machine learning model, you can just get to the endpoint like very fast, right? So you don't need to worry about it. Have you had thoughts about like, if that's the target, can you skip some of this? Yeah.
Yeah, I guess if they're solving for the equilibrium state, then it becomes easier. But if you're doing the time stepping model, then you're in transient hell.
Very nice talk, Deepak. So the properties you define are gonna prove that your algorithm is correct, but then maybe even though your algorithm is correct, some intricacies with the floating point operations might actually fail your property testing, even though your algorithms are correct. Are there mechanisms to maybe loosen those properties to take into account those kind of intricacies that you might not care much about?
Yeah, I mean, and first to clarify, it doesn't prove anything, right? It's just random testing, and it just gives you more confidence that you sampled more of the parameter space. And yes, I think actually a really valuable thing is you have to, because the test is very specific, so you have to say I expect this to hold to n decimal places. And I think that itself is also valuable. Like it forces you to be very clear about what your model satisfies. And sometimes you can get surprised. I've been surprised myself. It's like, this should work, but no, it doesn't work to that level. You have to do more work.
Thanks, Deepak, for great talk and finding the bug in the CSM OMSys configuration. Let's thank Deepak one more time. Thank you. The last speaker of the morning session is Annalena Deppenmeyer. Anna, are you online?
Yes, I'm here. Can you hear me?
Yes, we can.
Excellent. I'm going to share my screen.
Yes, please do.
So, by the way, after Anna's talk, we'll be taking a picture outside by the stairs before we break for lunch.
Anna will be talking about mixing it up in the tropical Pacific.
Yes, thank you, Gustavo. And thanks for inviting me. I'm going to talk about how Frank mixed up the scene in the tropical Pacific. And this is some of my work that I've been doing with Frank and also with Luann Thompson and Billy Kessler in the last couple of years, when I also had the pleasure of working with Frank. And I think Deepak already nicely summed up how it feels as a young scientist to work with Frank. So I'm going to just give you a little bit of an overview of how Frank influenced this work. And so the first thing I did is I Googled Frank. It turns out there's a concrete factory by Frank Bryan. And I figured that works pretty well if you just replace the concrete with ocean model or ocean knowledge. And then there's a 102-year change here in time when Frank joined NCAR. But so now we have our own brand of Frank Bryan factory. And we all know since Frank joined, he loves salinity. So from the very early days on, Frank has been fascinated and publishing impactful work on salinity. And he's been involved in field campaigns, so not only model work, but also designing and thinking about ways how we can best get information from the real world and then compare our models to, which I think is something that Frank and I have been working on in a little bit of a different field together as well. And of course, Frank then followed up this observational interest and work with the model study. And he came up with this really nice idea of how you can construct an isohaline salinity budget and how you can estimate the variability and the influence of different effects, such as mixing, but also eddy covariance on the extent of the salinity budget. And in this paper, he has this really beautiful picture, but of course we know that pictures aren't really what makes Frank tick. Really, Frank loves a good equation. So you can also find nice equations in this paper, and he manipulates those equations very expertly, as he does. I'm sure most of you know that. And now this is where his love of equations takes over and trumps his love of salinity, because he doesn't mind that salinity has to take a second role now in our work, where he realizes that these equations that he's used to analyze the salinity budget can also be used to analyze the temperature budget. And then there's a really nice formulation of where you can massage the temperature budget and arrive at an equation for cross isothermal velocities or a water mass transformation, where you can calculate the rate of water mass transformation and link that to the heat budget, same as with the salinity budget that Frank has done in the past. And this was the focus of our work over the last couple of years. And I'm just showing you this equation because I know that Frank enjoys equations. And to show you that we get this water mass transformation here on the left. I actually don't know if you can see my cursor, but that's the WCI here. And we can attribute it to the heat budget and drill down the individual terms that play a role in this temperature budget. And that's what we've been doing in the tropical Pacific. And I just wanted to give you a brief overview, even though Deepak also already mentioned the tropical Pacific. That's another thing we have in common working with Frank on tropical oceanography. And so in the tropical Pacific, you have this really strong equatorial undercurrent flowing along the thermocline towards the east. And you have upwelling in the east. There's also a westward current on the surface, which induces a lot of shear. So here in the middle is where the mixing it up really happens. So you get these mixing induced by these strong vertical current shears. And now we can equate this mixing and these exchange of properties to a rate of a water mass transformation in terms of temperature class production. And knowing the system, and I've already said here that we're mixing it up, so we're combining mixing and upwelling in this framework, and I've mentioned the strong current shear between the equatorial undercurrent and the south equatorial current that induces this mixing. And I'm going to show you basically what the equation gives you if you take the vertical derivative of the turbulent heat flux due to vertical mixing. I don't have the equation back on here, but that's what you do. You get the turbulent heat flux, you take the vertical derivative of that, and then you get the contribution of water mass transformation or WCI, cross isothermal velocities from vertical mixing. Another important component in this system is solar penetration that sort of opposes, in the derivative, opposes the turbulent mixing induced vertical heat flux, and you get a total of diabatic upwelling, which now really nicely ties the vertical mixing to upwelling. So a movement of water passes across an isotherm, and where we have a stratified fluid and the isotherms are horizontal, you get this vertical movement, so therefore upwelling. So this was this nice framework based on these equations that Frank used and that we used to diagnose from an ocean model, the diabatic upwelling and the contribution of mixing to it. And then if you look at the long-term mean, you can see that you nicely recover this shape that you could derive from thought experiment, if you will. And this is about a third of the total upwelling, this diabatic upwelling. So it's significant contribution to the upwelling, which again is maybe going back to older oceanographic concepts where you think of equatorial upwelling. And then you usually think of sort of water diverging on the equator and then replenishing from below. But a third of this is not only an adiabatic movement, but a diabatic movement that actually takes heat into the ocean. So really mixing it up or mixing heat down in the tropical Pacific. And this is just another illustration that if you plot them on the same color bar, you can see that this diabatic upwelling is a third of the total upwelling. Frank's also always interested in variability, so we then investigated how this diabatic upwelling varies on different timescales, and the big one in the tropical Pacific is obviously the El Niño Southern Oscillation. We found a significant variability with the different ENSO phases, that also resembles still this theoretical shape of the diabatic upwelling, but you can see some significant changes. And if you look on other timescales, such as the seasonal cycle here on the left, or the tropical instability wave, so timescales and phenomena, you can see some significant modulation of these properties here too. And we can again attribute these to the physical mechanisms behind them, which mostly are vertical mixing in the interannual and seasonal timescale, together with solar penetration. And on the tropical instability wave timescale, you also have vertical mixing, but you also have eddy covariance, which I believe is something that you have heard about and will hear about more today, because that's another thing that Frank loves, a good ocean eddy. Okay, so this beauty of equations, that we can calculate this diabatic upwelling from the thermodynamics, as we've done in the past and in the last couple of years, also gives us another way to calculate diabatic upwelling, and that is integrating the kinematic equation. And if you do this right, then you're supposed to be getting approximately the same thing, not entirely the same thing, especially not at the surface, but approximately the same thing of diabatic upwelling. And so this is another thing that Frank realized, because again, Frank's always been interested in creating or thinking of good ways to measure the ocean and confront our ocean models with it, with the measurements. And so this would be a nice way of being able to get to this diabatic upwelling and therefore get through the heat budget to different kinds of measurements. And so we have tried to do this in the ocean model, and then I already said that they're approximately the same thing, but not quite the same thing, the kinematic and the thermodynamic diabatic upwelling. And you can see that here, where we have them next to each other, kinematic in blue and thermodynamic in orange. And where you go below the thermocline, you see that they really nicely match, and actually match, well, I'm not really sure what to say, decently well if you look in this temperature class, with observational estimates that are derived from the kinematic upwelling. Don't match quite so well down here. This is a problem of negative upwelling or downwelling that has been derived from observations or box models, and we have looked for extensively and not been able to find it in the model. So mystery to be solved. But you can see that in a long-term average, if you look at a region around and below the thermocline, this diabatic upwelling from kinematic and thermodynamic theory matches really well. Again, thinking about this observing system, how could we observe this? We've then tried to look at one point, but not, in this case, 36-year average, because we might not have 36 years worth of observations. So we've looked at an averaging in space. I believe these are several dots up here that we averaged, where we could maybe construct a mooring array to get to these quantities. And you can see that sort of the longer time scale variability agrees, while there's some more noise in the kinematic over the thermodynamic estimates. And then if you average over some time, so you introduce a running mean together with some spatial averaging, you get those to match better. And these are some of the things that Frank and I have been thinking about. How could we get to this crucial quantity in the Pacific Ocean that plays a role in heat uptake and redistribution eventually of heat into the ocean? And so this is all diagnosed from an ocean model. I really should have put the Frank Bryan Ocean Model Factory logo back on here, because of course this is introduced from an ocean model. Just showing you here the 10th of a degree forced global ocean simulation, the part that we've been looking at. And you can see these beautiful eddies here in the central tropical Pacific that, you know, we know Frank loves a good eddy. Fun fact, we've also written a proposal to maybe look at these eddies that are happening up here, more in the northeastern part of this domain, which unfortunately hasn't been funded, but otherwise we would have looked at more eddies with a similar sort of framework. But we also know, and Deepak has said this too, is that there's a mixing scheme that parameterizes the mixing, which I've just said is so important in this ocean model, and the ocean model is biased. So if you look at the contribution of this mixing scheme to the seasonal cycle of sea surface temperature, here in black, the seasonal cycle of sea surface temperature as observed, and here as simulated by POP, so this was POP. Can make a similar figure for MOM. I did not put it on here, but it exists. you can see that the contribution of vertical mixing here in blue in the observations is overall has a larger seasonal cycle amplitude, but is overall lower. So there's more cooling induced by vertical mixing in POP than in what we see in the real world, and the ratio between cooling by vertical mixing and this heating by the surface flux is not quite the same as it is in the real world. So we know that our ocean models are biased, and I think it would be really great to write a unit test or I forgot the word, sorry, Deepak, but I think I'll leave that to Deepak. So instead, I'll be using data to look at these model biases and see whether we can do something or whether we can find out where the biases are based on observations. And so we have this data set of turbulent heat fluxes that was also used in the figure that I've just shown you, vertically resolved and resolved with the seasonal cycle here in different colors. And we can make the same figure for an ocean model, and we can see some differences here. So overall, the magnitude of the vertical mixing shifted towards the right, which means it's higher. That's something you've also seen from the other figure. And you can also see that the seasonal cycle amplitude is smaller in the model than we see in the real world. So what is the conclusion of this? Well, this could have an impact on the sea surface temperature. If you have too much vertical mixing, you would be drawing down too much heat and cooling the sea surface temperature. So something to be investigated. But in order to do that, we really need more measurements. So we need to be able to look at mixing and its impact on the sea surface temperature, especially in this region, in more detail. And so this is something that sort of follows along of Frank's work of thinking about spurs and thinking about grace, and thinking about observations and possible observing systems and how we can match them to our models and therefore improve our models. So we are working on designing this field campaign that will gather observations that will then let us go through the hierarchy of models to see if we can improve the parameterizations underlying, in this case, the vertical mixing, but there's other parts of this project too, underlying in the ocean models. And so something that Frank and I have done, and I wish I could show you a whiteboard photograph. I've been scrolling through my phone. I know I have several of them. But what we've done is we've looked at how can we possibly design a mooring array that would allow us to best observe these properties and these quantities that we're interested in that would help us improve the ocean model. Would this be a good configuration? Or maybe this would be a good configuration on these underground things here are, oh, I don't know what happens here, what happened here, are autonomous vehicles. But yeah, this is giving away the punchline. So basically we need more Frank Bryans. We need more people. And ideally, Frank, like Deepak, I'm also trying to rope you in and keep you engaged. We need more of your thoughts to design this campaign and be able to fully utilize the outcome too. Thank you. And I'm going to have to stop sharing and make the screen smaller because I can't see any of you otherwise.
Thank you, Anna. We have time for a few questions.
Hello, Anna here from the Met Office in the UK. One question. I don't know if it's possible, so I'm not offering because I'm not sure if we can share, but would you be interested in looking at operational output, so output for that region from an operational coupled system?
Yes, absolutely. I would be interested. And I don't know if you noticed, but I've just actually made the move from NCAR to the University of Liverpool in the UK. And I will be working on this field campaign for the the implications in models. And I'm interested in looking at different models and how this impacts, how this plays out in different models. So I would love to get in touch and start those collaborations.
Okay, thank you.
Any other questions?
Yeah, thanks for the talk. This is Stephen Griffiths. You mentioned when you were doing the kinematic and thermodynamic calculation of WCI, I think you called it, that they are not quite the same. I mean, you can write them down mathematically as identical. What is it that's different? Is it just the calculation numerically that you're having differences, or Am I missing something?
Yeah, so that's a really good question. So the detail here that I didn't get into is that for our thermodynamic estimate, we project the velocity into the direction of the temperature gradient. So the kinematic estimate is always going to be vertical because you derive it from movement of the isotherms and in and outflow of water in the isothermal layer. So it's going to be vertical. But our thermodynamic estimate, when you get really close to the surface where the temperature stratification is not horizontal, but it's vertical, is actually not an upwelling anymore. It can be, in the case of the equatorial cold tongue, a meridional motion because it will go into the direction of the biggest temperature gradient, which in that case will be meridional. So just where you get close to the surface, they diverge by the way that we calculate them.
Okay, let's thank Anna one more time.
Thanks, everyone. Enjoy your lunch.
And we will now take the group photo outside.
If you can take your seats, we'll get started. If you can take your seats, we'll get started. Okay, so it's almost 1:30, and I know that quite a few people had to leave to catch flights. Peter and Steve. They're talking about friendly competition, apparently. So we'll have start with some remarks from Mike Whitney. Are you there, Mike?
Yes, I am. Can you hear me okay?
Yes, please go ahead.
All right. Thank you, Gökhan. Well, I just have a few remarks, some from our student, Chen's son. It's great to be part of the ceremony honoring Frank and NCAR. I thank Gökhan for the invitation. It's been inspiring all morning to hear of the accomplishments and stories of NCAR and Frank, and I look forward to hearing more. Frank certainly has earned far-reaching respect as well as warm feelings and friendships. NCAR is held in high esteem for its scientific leadership and its engaging community-building ethos. Frank is a wonderful ambassador for NCAR in our field. His inviting nature welcomes us all to collaborate. Everyone knows he's brilliant and incisive, but he'll never say that. Instead, he's always listening and helping while guiding us along good paths that lead to great outcomes. Frank also mixes pragmatism and humor to navigate bumpy roads along the way. He's a great scientist, leader, mentor, and friend. He's wonderful. I met Frank years ago when I was in town for a UCAR meeting. I came out to the Mesa basically on a cold call because I had some thoughts on how estuaries and river plumes could be better represented in our system models. Frank didn't know me, but he welcomed me, and we had a great conversation. That inviting start ultimately led to a proposal, Department of Energy grant, the estuary box model that's now in CESM, and publications. Frank guided us in turning those early ideas into a reality. Very important. What's been truly meaningful to me are all the visits to NCAR, all the discussions and help along the way with Frank, Keith, Young, and many others. The NCAR lunches, which I know I just missed, and the relationships. And also being welcomed as a coastal guy into a climate modeling realm. Frank's mentoring of our PhD student, Chen's son, was truly invaluable. My family came with me to Colorado for several weeks for a couple of summers. My kids were young back then, and it was a magical place for them. My youngest believed Colorado was its own country, and NCAR was the castle on a hill. I'm pretty sure that made Frank a king in their eyes, or definitely nobility. And Frank's meant, and which fits very well scientifically, I think. As an aside, I eventually took to stand-up paddleboarding because of Frank. I find it mostly enjoyable, but sometimes I don't live up to the stand-up part. I have a feeling that Frank has avoided that problem by numerically solving the stability analysis. As for me, I'm still suffering with episodes of, let's just say, rapid potential energy loss. At this point, I'd like to read some heartfelt comments from Chen's son, our PhD student who is now a researcher at Tulane. Frank was a pivotal member of my PhD research committee. His support and encouragement were instrumental in my journey to becoming an oceanographer, particularly shaping my research focus on the connections between riverine freshwater runoff and global ocean circulation. My background was rooted in coastal research. Transitioning to the complexities of the open ocean posed significant challenges for me. My PhD research aimed at improving the river discharge representation in CESM. This task was technically demanding and required advanced skills to implement the subgrid scale estuarine parameterization for over 2,000 rivers in the CESM ocean component. Frank's support was unwavering through this process. We had weekly meetings during the semester, and he facilitated an internship opportunity at NCAR. Beyond his technical mentorship, Frank motivated me to develop observationally based metrics for evaluating global climate model performance in coastal regions. This largely shaped my perspective on interactions between coastal and open ocean systems. Thanks to Frank's mentorship, I successfully transitioned from coastal engineering to oceanography. His impact on my research approach and understanding of ocean dynamics continues to be profound, and I still draw on the insights and skills I gained from his guidance. Thank you for those kind words, Chen. So we all know Frank has helped many others in similar ways. He helps us all grow and achieve together. I'll add what Chen was too humble to say, that he received the 2018 CSM Graduate Student Award for his accomplishments. Chen's a wonderful colleague and has grown into a leader in his own right too. Now, Gustavo, Chen, Melissa, and I are working forward to working together with Frank on our new NOAA map project, seeking coastal advances in Earth system models. I'm implicitly assuming Frank will just keep on engaging in science into the foreseeable future. After all, persistence is a valuable benchmark in modeling. And as in our interconnected Earth system, the things Frank has set in motion continue to ripple through our field and have long-lasting and far-reaching positive effects. Frank, I'm grateful to be counted among your collaborators and friends. You're an inspiration. Thank you.
Thank you very much, Mike. That was great.
You're welcome.
You're not taking any questions, I guess.
I could, but
yeah. What's the deal with this cherry box model? Okay, thank you. So we'll go ahead with our first speaker in the room this afternoon, and that's Dai.
Thank you very much. Thank you, Chairman. So, thank you very much for to give me an opportunity to talk about the NCAR creative collaborations. My name is Dai Tsumune. I'm just moved to the University of Tsukuba, but still have appointment with Central Research Institute of Electric Power Industry. So we call CREAPI. And so we talk about another aspect of Frank's archivement with us. So NCAR creative collaborations more than 30 years. So 20 years with oceanography sections. So the collaboration object of the collaboration is to train the creative scientists in the use of CESM and aid in the adaptation and transfer of NCAR developed modeling. So NCAR technical representative is Frank Bryan, and now is Keith Lindsay. So we are long-term visitor, me and Kaz and Takaki for oceanography sections. So our family is very enjoyed living in Boulder. So because of the Frank and Catherine and Ophelia, thank you very much. And so other people is also coming. So CREAPI is a non-profit organization to serve as a comprehensive research for electric power industry. It's funded by electric power industry in Japan. The climate change was one of the big issues for electric power industry in Japan. But since Fukushima Daiichi nuclear power plant accident in 2011, so CREAPI research is expected more to contribute more directly to the electric power industry. So we moved to the radioactivity in the ocean. But Kaz missed me continue to study oceanic ion modeling for science by other research funds, but as a proxy of a plutonium isotope modeling in CREAPI. So he explained. So we focus on the reconstruction of the cesium derived from the F1 accident. So using the atmospheric modeling, the regional modeling, and the spatial modeling, and so on. And to understand the contamination process, seawater, marine biota, and sediment, and so on. So at first, we employed a regional ocean modeling system from NCAR. So this is coastal to open ocean area. So 600 meters and 450 kilometers. So here, yes. Here is a nuclear power plant is here. So so horizontal resolution is 1 degree. Its resolution is high in the regional ocean. But today's talk, so already done 1 kilometer degree and global ocean modeling. I'm very surprised that. So maximum depth is set to be 1,000 meters. So because this is a huge trench, more than 10,000 meters along here, to reduce the cost of the computational resources. And also we employ the driving force, a realistic driving force based on the reanalysis data, Japan Meteorological Agency, to represent the coastal current, north and south. North-south component is dominant. So it changed every 3 or 4 days by synoptic time scale. So we apply the observations by ADCP just in front of 1F by here. So red shows the observations, blue shows the simulations. So quite in good agreement of the observations. So, and also we also data simulation nudging as suggested by Frank. So based on the ocean reanalysis data, JCOP2. So we can represent the cross-shore current and mesoscale eddy and so on. Here's a comparison between the satellite data here. So we can success to represent the oceanic current in front of 1F site. So when we look at the temporal change of the cesium concentration here, so this shows the cesium concentration right after the accident. So highest value is 68,000 cubic meter, becquerel cubic meter, and then decrease quickly. So here is apparent half-life is 1 year. And also after 2016, decreasing trend is stopped here, almost constant. The value is still 1,000 becquerel per cubic meter. So this value is still 100 times higher than previous levels. So due to the atmospheric nuclear weapons test. So this means, so direct release still continue now. So it's very big problem for the decommissioning of 1F. So we try to find, but sources of release of cesium is still unknown. We have to take care of those things. So anyway, so we are using the estimated release rate. We try to consider the comparison with observed data. Magic one. Thank you. Yeah. So when we looked at the daily average field, so very complex feature. This is a map and the enhanced map here. So due to the changeable coastal current and mesoscale eddy. So it is difficult to compare with the simulation and observation because observation is a very snapshot at each point. So we looked at the annual average field. So this each point is every 1 week or 1 month a day. So we can obtain the annual average concentration by observations. When we looked at annual average simulations and observations, so relatively in good agreement with observation. So comparison with the annual average field, so our model can validate so accuracy of the so comparison with observations. So we apply the discharge of Alps treated water of these models. So radioactive contamination water continue to increase due to the groundwater flowing into the damaged building at the 1F. So there was a major issue in the decommissioning of the 1F. And radioactive materials is a contaminated water are removed by the, we call it ALPS systems, but tritium cannot be removed. The plan was to dilute the tritium in the ALPS treated water and discharge into the ocean since 2012. But so there was a great concern to the ocean discharge of treated water from the power plant that caused by the accident. So TEPCO is a Tokyo Electric Power Company who operates the Fukushima Daiichi Nuclear Power Plant, was required by the Japanese government to publish the radiation impact assessment. So our model was applied to the, this impact assessment. So here is one of the results of the TEPCO's result, report. So affected area is quite small here. So because of the existing of the background concentration of tritium derived from atmospheric nuclear weapons test, the levels are 0.05 becquerel liter and so on. So those assessment results from ingestion of the marine products, etc., are negligible. And IAEA reviewed TEPCO's report is okay. So ocean discharge of ALPS treated water started in August 2026. So after planned, more than 11 years after first plan. And so validation is important. So release rate of the ALPS treated water is published in real time from TEPCO. So relatively much monitoring has been carried out. So here is a monitoring point. So it was considered very useful to assess the skill of ocean, regional ocean models. However, the current release rate are smaller than regulation have not been yet effectively validated. So we need, I personally think so more release rate is better for the ocean science, I think. So here's the result of the, here's the observed point is here. And contour is the simulations. So relatively in good agreement with observation, but still different each other. It is still compared with a snapshot of each. So when we move to the talk about the global CGM simulations with Frank and Keith recently archived. So based on the International Atomic Energy Agency, so IAEA Corporate Research Project. So we called RAMEL, so named by the French guys. So its object is to develop the applied data compiling the modeling methodologies and determine the level and so on of radionuclides in the marine environment. The result will provide a comprehensive and reliable baseline of the radionuclide concentration and compared with the future change. So since observations alone are not sufficient to determine the baseline, so global simulation was performed. So results are useful planning of the future observation, I think. So we already, so last year we published. So it spent a long time, so more than 5 years. Thank you very much, Frank and Keith. And so here is the input of CGM of the global ocean. So main input is global fallout. So 5 petabecquerel. So I usually experience the peta, but so everyone knows that the peta, familiar with the petabyte. And so Fukushima Daiichi Nuclear Power Plant, 15 to 20 and several petabecquerel, atmospheric deposition and direct release. And the discharge from reprocessing plant is 41 petabecquerel here. So this is atmospheric deposition pattern is here. So we construct based on the GPCP precipitation data here. So high in the north hemisphere, low in the south hemisphere. It's very similar pattern to accident. So here is observed simulated surface cesium concentration in 1960s. So relatively higher concentration is observed eastern part here. So even if a deposition is large in the western part, So this is due to the transport by the cross-show current, and also difference between the mixed layer depths. So low in the west, high in the low in the east, high in the west, and so on. So comparison is relatively in good agreement with observation. But so this scale is a log scale. So still need to more accurate simulations and so on. So after 1970s, 80s, 90s, 2000, so observation is just started here along the Scandinavian peninsula after the discharge of the reprocessing plant and so on. But distribution pattern is getting homogeneous, and also fewer observation points. So it is difficult to find the baseline, so current observed situations. And when we looked at after Fukushima accident, so too many observations is carried out in North Pacific area, but few in other oceans. So not so interested in the cesium concentration other basins. So it is very difficult situation to make baseline levels. So we'd like to confirm this concentration level by future observation plans. So this is still bias along the cross-show coast because due to the Koji resolution model. So we also employ the higher resolution model. So Takaki Tsubono is developed this modeling by using the ROMS. So with Frank, so during his longer term stays. So more accurate simulated result is occurred. And also he applies based on the global fallout. So this paper is still in preparations. So we need to more accurate. And also when we look at the North Pacific and North Atlantic, so each layer, surface and intermediate and deeper layer. So point shows observations. So color shows simulations. So relatively in good agreement observations. So in the North Pacific increased due to the Fukushima accident. And the North Atlantic increased due to the discharge from the reprocessing plant. So when we looked at a deeper layer, so very different situations. So deeper layer is existing cesium due to the deep water formations. But in North Atlantic, there is no observed data recently. So we need some observation in the future. And the North Pacific Ocean, so there is still observations. So this is influenced by the contamination due to the old large volume water sampling techniques. So care should be taken into data use. So finally, so as inventory cannot be obtained from the observations, so analysis was carried out from the model's result. So this is due to the global fallout, so increase due to the Fukushima accident. So North Pacific area and the North Atlantic area. North Atlantic area reduced to the half-life is 30 years, but so due to the discharge of the reprocessing plant, so temperature changes are very different from North Pacific oceans. So finally, so through the 20 years collaboration, CREEPY has introduced ocean models from NCAR. So application of the ocean modeling from NCAR, so CREEPY has been able to make contribution in the area of the nuclear power plant accident. So this is largely due to the Frank Bryan's contribution and his kindness. So we are grateful to his patient as he has worked with us. Thank you. So from now on, collaboration is began with Keith Lindsay. So, and basic research is also important for young science in CREEPY. So we hope the marine radioactivity modeling research will contribute to oceanography section. Thank you for your attention.
Questions for Dai? I hope Keith knows what he's getting into with all that.
Sorry, just a maybe technical question. You showed all these observations.
Yeah.
Also the Atlantic. What kind of program is making all these observations?
These observations.
Yeah.
Formally, so WOS is one of the pointers.
WOS.
WOS project.
Yeah, but that's long ago. I mean, basically, you have all this cesium now or whatever in the surface Atlantic. Who's measuring that?
Here.
Yeah, the more recent observations, who's providing those?
Here.
The upper right panel, for instance, you have the Atlantic surface observations.
Here. So mainly along the coast of the peninsula.
Okay.
Yeah. So, and also one observation is occurring here. This one is Japanese scientist. So no program for the cesium.
So has polluted water from the Fukushima plant now been started to be released into the ocean?
Yeah. So still problem. So larger than treated water release, I believe, but no one knows. So Japanese government published so officially.
Yeah. So you expect the concentrations to remain high for some time because that releasing will go on for many years.
Yes, that's right. So this one is still higher than. So this result is showing. So they did not explain about the.
So you said it's still 10 times higher than normal?
100 times higher, yeah.
Okay. Is it harmful for the humans?
Pardon?
How much fish can you eat, I guess? That's
yeah, fish level is along the, here, 10,000 becquerel per cubic, 1,000 cubic meter. So this is a level of the attention to the fish. So still okay, but problem. Yeah.
I guess following that, is there a particular kind of fish with more concentration of cesium?
Yes, yes.
All equal?
Yeah, it depends on the fish species.
Species.
Yes.
Okay. No sushi. But
Yeah,
no, we
yeah,
need to know which kind to eat, I guess.
Yeah,
that's what I was asking.
Eat.
Okay. Safe travels to GFDR, folks.
Thank you.
Safe travels. Okay. Any more questions? If not, thank you, Dai, again.
Thank you very much.
The next speaker is Justin, I think, right? Yeah.
Thank you very much.
Go next.
Oh, I didn't have to do anything. It just came up. That's great. Okay.
Am I here? Oh, I'm here. Okay.
So it's there, not here.
Thank you. I'm glad to talk at this anniversary and to thank Frank, who's not here right now, but hopefully will be back. And I'm going to talk about some work which started from Frank's contribution, but also many other people that I've listed, and I didn't try at the pointer, there you go, that I've listed here. I remembered I forgot also Keith Lindsay helped me out with a lot of the tracer budgets that I'll be talking about here. So the topic is upper ocean heat and salinity budgets from high resolution models and data. A subtitle, when is a high resolution model like a low resolution model? That might sound like kind of a silly question, but I'm gonna talk a little bit about that. And let's see, okay. And I'm going to talk about some air-sea interaction problems, which Frank was interested in, and I was interested in, and there was a long history of the theory, and there were new high-resolution models being developed, and we'll hear more afterwards, and there's been talks already. So air-sea interaction, there's been coupled stochastic models, and an example is from Barsugli and Battisti in 1998. And the idea was that you had these coupled equations, one for the evolution of atmosphere temperature, number one here, one for the evolution of ocean temperature, and they're related, and there's a dependence on the air-sea temperature difference, which is termed in brackets. This is the turbulent heat fluxes with coefficients before them related to the feedbacks. There are damping terms, which are these gammas here. And the key thing is there's noise or stochasticity. And initially, it was introduced as atmosphere noise, which is this NA. And then later contributions added ocean noise, NO. So the atmosphere noise might be the weather systems and so on. The ocean noise, the natural variability, such as mesoscale eddies. So there were papers following on from that, Wu and Kirkman et al., Stu Bishop and Frank and myself, looking at that. It was learned afterwards that these equations seem to be too tightly coupled, and if you use the kind of coefficients recommended by the papers, the feedbacks were too weak and the atmosphere temperatures were not very realistic. What was then moved on to was to go back to stochastic ocean mixed layer models. So this now is not coupled. This was started by Hasselmann and Frankenmuhl. And my collaborator, Lucas Lorindo, who's worked with Frank and myself and others, and with Luann Thompson, had some nice study using an ocean mixed layer model. And now atmosphere noise is in the air-sea flux term here, the NA, and there's a damping, and there's an introduction of ocean noise here. Now, what I'm going to show in the next slide is what does the system look like typically when you have various levels of atmosphere noise versus ocean noise. If you have high atmosphere noise, it'll be atmosphere-driven. If you have high ocean noise, that's the ocean-driven. That's what I'm going to illustrate next. This comes from a paper led by Ben Kirkman, but including a large contribution from Frank and the people listed at the bottom here. And it's point-wise correlations between SST and in the top left here, turbulent heat flux is TH flux. This is from low res. So on the left are low res plots, and on the right is from high res model. And the top panels are SST and turbulent heat flux. Where it's very positive is where the ocean noise is dominating and is driving the turbulent heat fluxes. So there's a high correlation between the SST and turbulent heat flux. That's seen in the high res. And if you look in data like Jayafuru, OA flux, and so on, it's similar to this, just a little bit weaker. Then for the low resolution model, it's got less of that signal, apart from in the equatorial region. So there's less of the ocean noise driving the heat fluxes, which you might have expected. And then the lower panels are between SST tendency and turbulent heat flux. So if you have a negative value here, I should point out, in the top panel, positive heat fluxes are out of the ocean in this definition. Here, if you look at the SST tendency and turbulent heat flux, the negative means atmosphere forced. And it's like if you force a bulk, a slab ocean with heat fluxes, you will get the negative correlation between SST tendency and turbulent heat flux in this definition. And so the low resolution is kind of tending towards the atmosphere driven. It's got a lot of blue, which is negative. The high resolution is much weaker blue. And in certain regions, like the boundary currents, it's near zero. So the tendency is not being driven by the atmosphere heat fluxes. Instead, the the SST from the ocean is driving the heat fluxes. So this was a major result that came out of the high-resolution modeling of CSM and its predecessors, which I'll mention in a minute, as well as the theory and contributions from people like Frank. So the question I'll try and answer in this talk is, what drives the SST variability that is forcing the SE heat fluxes in the high-resolution model and in the observed data in a lot of regions of the globe? And the method I'll use is upper ocean heat budgets. There'll be a follow-on question. Hopefully I'll get time to talk about this. How does this compare with other tracers? So I'm going to look at upper ocean salinity budgets. Salinity does not appear directly in the air-sea flux formula, unlike ocean temperature. So there's no feedbacks operating. So this will likely change the results. The other reason I'm looking at NASA, at salinity budget is NASA is funding. And the NASA salinity science team is funding current work on salinity budgets. So thank you to NASA. The approach, I'm going to use an Eulerian method. I'm not going to use Lagrangian control volumes, which Frank has used in some other work. And I'll just, if anyone saw Steve Griffey's talk, Lagrangian is actually Eulerian 2. If you didn't see that, it won't make much sense. I'm going to use grid point regressions, but I'm going to learn about space and time scales just using spatial smoothing. And a key contribution from Frank to this field was, it may seem like it's fairly obvious, but people weren't doing it, to distinguish different spatial scales and see what's happening and reconcile differences. To, for example, reconcile data taken at a single point and data from a larger volume or grid cells or so on. And I'll show one example later where I look at seasonal cycle in the subtropical Atlantic, where that comes in relevant. And I will be looking at non-seasonal variability. I will skip and say I'll hopefully look at a long-term annual mean, that'll be for salinity and seasonal cycle. Some of the plots will be regressions of tracer tendency on budget terms. And in these plots or maps, values near 1 mean the budget term is dominating. If it's 0, it's not. Okay, diversion now. The one stressful moment about working with Frank. So everyone said all the nice things. It's not that bad, Frank, don't worry. Frank was my supervisor for almost 10 years, which I class as unlucky. Gökhan has that joy now. A quote from Frank, "You've got 2 hours to learn water mass transformation theory from scratch." I didn't know about it. "In order to make this proposal on time." This was probably mid-2010s. This is not an exact quote. I've probably forgotten some details. I did not succeed in learning water mass transformation theory in 2 hours. But we did make the proposal on time. How we did that, Frank wrote the water mass transformation part, which seemed to be the most reasonable thing to do. Myself and Stu Bishop wrote the other parts of the paper. I think there were about 3 parts. One was a water mass transformation. And as a side, that came from this correlation between SST and heat flux. That was where the water mass transformation came in. So for me, learning water mass transformation theory is a major thing for my career, I think. It enabled at least one extra project to be funded from NASA again. So it was worthwhile. And there were 2 papers, one published, one nearly submitted. I'm working with Dan Witt, who's in the audience, and Ivana, and there was some help from Ben Johnson early on. Okay, I'll talk a little bit about the model, but I think we've heard a lot about this, and probably the next speaker, Julie, is the expert on this, and I'll talk more. But I'm using a class of the high-resolution CSM, and the history from that went back to about 2000 and earlier, looking at other resolution. But for the 10th degree, 2000 paper by Rick Smith, Maltrude, Frank Bryan, Matthew Hecht. And then the following paper That was a regional model, then the global model by Maltrude and Julie McLean. And then 2 papers of coupling came out similar time from Julie and from Ben Kirkman, 10th degree ocean with 1/4 degree atmosphere or 1/2 degree atmosphere. And then afterwards, there was a suite of papers where we used 10th degree ocean and 1/4 degree atmosphere with CAM's spectral element, which enabled it to be run faster, and the ASD run and the IHESP and Maserclip and so on. It's been a lot of, and IPOG, it's been a lot of development. I will compare high-res CSM and low-res CSM. I'm not going to explicitly state what are eddies or not. And I will say that there's high-res has lots of other differences with low-res, better resolving mean flows and due to better bathymetry and so on. I'll skip over the quote. It wasn't as funny as I thought. I'll move on. These are some of the results I was talking about earlier, so now getting back to the results. This is heat budget to 50-meter depth in the ocean, and I'm regressing the tendency on budget terms, and top left is tendency and vertical diffusion, and I include the surface flux in my vertical diffusion term, and that dominates. So in the low resolution, values are near 1 over a lot of the globe. The tendency is driven a lot by vertical diffusion, mainly surface heat flux. We saw that in the earlier slide. On the top right is tendency and ocean heat flux convergence, and it's much smaller, as you expect. And these 2 in combination should add up to about 1. On the bottom is the high res. The tendency and vertical diffusion now is much weaker, as you can see, and instead tendency and ocean heat flux convergence is near 1 over a lot of the globe. So it's dominated by ocean heat flux convergence. So I'll just say this monthly data, grid point regressions from a closed heat budget. Some of that advection, or ocean heat flux convergence, is atmosphere driven, quite a lot really. For example, Ekman heat transport. This is winds acting on SST gradients. And on the top we have, for the low res, a regression of ocean heat flux conversion and Ekman heat transport, and you get some quite large values. So the winds are doing a lot in the low res. In the high res, the values are smaller, but you can see some regions where, like Southern Ocean, where it's having an impact. I'll come back to that. Number 3, what happens if you smooth the data? So I've shown you already, top left is high resolution. This is between heat content tendency and ocean heat flux convergence. So it's high in the high res. If you go to bottom right, sorry, the pointer's slow. In low res, it's weaker. Now you successively smooth or coarse grain the high res to, I'm going to give up on this, to 3 degrees, spatial scale box of full width 3 degrees, 5 degrees, 7 degrees, and 10 degrees. And now you see that the high resolution model is looking like the low resolution model. There are some differences, and for some metrics you see differences, particularly in the boundary currents, but they're the same model, but with more detail in the high resolution model. I find that kind of reassuring. You don't want the high res to be completely different to the low res. And another aspect of this, the Ekman heat transport, I showed these 2 panels previously. Now, if you spatially smooth the high res, you get this result on the right, and you'll see it looks somewhat similar to the low res. So even in the high res model with lots of eddies and variability due to eddies, there's an underlying Ekman heat transport, wind-driven, large scales, similar to low res. So it's a question of scale, and the paper by Stu Bishop also looked at various different scales in a nice way. And also Lucas Lorindo's written some nice papers. He was a postdoc and an ASP postdoc here for 2 years, now at the University of Miami. This is actually his recent paper that we worked on salinity. And this was looking at the budget for salinity, and I'll talk more about the budget in the next slides. But this just shows a comparison of variance of sea surface salinity from different products. Monthly data, and you have OI SSS, optimal interpolation SSS, that's got from satellite salinity here. Then Argo, and this is a product that Lucas derived from Argo data. It was shown in an earlier talk. Low resolution CSM and high resolution CSM. And if you look closely, you'll see there's some similarities, particularly between high resolution CSM and Argo, say in the Southern Ocean, if you look at the spatial structure, also in some other regions of mid-latitudes. Yet, the satellite data has deficiencies, particularly in high latitudes, which is known where the temperatures are cold, and the low resolution model has too weak variability, e.g. in the Southern Ocean. In the annual mean for the salinity, you have a balance between the surface freshwater forcing, which is shown here, the subtropical highs and the ITCZ, and the balance with the advection, which is shown here. Diffusion plays a role. Here I just mean diffusion at the base of the layer, not the surface. And the tendency here is much smaller. This is an annual mean plot. Then if you look at seasonal cycle, this is a time series in the subtropical Atlantic spurs region. And previous papers said the seasonal cycle, particularly in the summer, is driven by surface heat flux. And it's more or less true in our model. When you spatially smooth to 10 degrees, tendency is shown in these blue boxes. Surface heat flux are these black triangles. So the black triangle does play a big role. So does advection. And this is actually surprising, because when you look at non-seasonal variability, I think this might be my final results slide, and do these regressions like I showed earlier, the tendency on terms like surface flux, vertical diffusion including surface flux, that's the residual, is totally dominated by this 3D advection or flux convergence. So if you look at non-seasonal variability of salinity, is on the grid scale dominated by 3D advection. But this is the same model that if you look at the seasonal cycle in the subtropical Atlantic, surface flux has a big contribution. So you're looking at different scales. This is a larger scale, 10 degrees, and different time scales. This is seasonal cycle. The other is non-seasonal variability. So you have to kind of dig out all the different scales and things because the behavior is different. Another thing I shan't talk about, there's a difference if you look at salt content versus salinity, and that'll probably be of interest to just a few people, but it actually makes a difference in the model because it has a, POP has this linear free surface thing, not as advanced as MOM6. I think I've come to the end of my talk. So I'll just say thank you to Frank, thank you to the ocean section. Thank you.
Any questions for Justin?
Hi, Justin. Nice talk. I just want to ask a technical question about this exact plot here. I guess I think of precipitation as being very episodic and in some places quite strong. And so I'm wondering, having a strong effect on SSS on a very transient basis, but you don't see, even in the ITZZ, any indication of that. Maybe that's just because it's monthly timescales. Can you comment on, or maybe because it's the 50-meter integration, or why is precipitation never appearing here? When would it appear at which scales? So on. Maybe I think it's hard to answer, but
yeah, the monthly time scale is one thing. I'm sure it's more important on transient synoptic scales. There was also a difference when this is for salt content. If you look at salinity, there's a slightly bigger role for surface flux. And if you look at larger scales, there's a bigger role. This is the grid point regressions, and things like eddies are dominating. But I wanted to show that annual mean picture and that seasonal cycle picture to show surface forcing does have a big role. Before I showed this, which is the non-seasonal, and it shows it doesn't have a big role. But yeah, this is work in progress, but things like looking at different scales and I'd say shorter time scales, you'd have a bigger role. We saw that with the temperature budget and the temperature correlations. When you went down to daily data, say in boundary currents, it was more dominated by the atmosphere for daily data than monthly, a lot more.
Okay, no more questions? Okay, our next speaker. Thank you, Justin, one more time. Julie McLean is our next speaker.
Yeah, I know. Okay, so I probably should retitle this as basically a retrospective trip through high-resolution modeling. But you know, we always want to define what high-resolution means. So in this case, we're talking about when we're explicitly resolving mesoscale eddies. So my talk and Detlef's talk has some information in common. So I want to go back to the 1980s and talk about just before the WOS period, when we started to see mesoscale variability emerging in some of our observations, such as from drifter tracks and from satellite products. So over on the left, you're seeing drifter tracks in the North Atlantic, and this was from approximately from 68 buoys. And then down here, you're seeing a field of eddy kinetic energy that was constructed from the buoys, showing the path of the black lines show the North Atlantic current path, making the northwest corner turn. And then at the same time, from the satellite products, as was shown this morning, from GeoSat, we started to get we started to see for the first time these well-known patterns of variability. So, as was mentioned this morning, the CME effort was designed as part of WOS to complement what was going on with the observational program. And Frank was very much involved in the formulation of this model, running it, and analysis. Of course, it was eddy permitting. And I think, as Detlef said this morning, everyone was saying it was mesoscale resolving. But it did give us a first look at mesoscale eddy processes, and was used widely in the community. There was a meeting at Princeton, I think in March of 1989, and I think that's the first time I met Frank. And a whole lot of people were there talking about their projects. And I actually used it in my PhD thesis to look at North Equatorial countercurrent eddies. So, but at the same time, Bert Sempner and Bob Chervin had they had developed the parallel ocean climate model, which was a Bryan and Cox derivative, and it was half a degree with 20 vertical levels. And you can see in this instantaneous velocity field over the top 135 meters, just the richness of the eddying motions. And this came out, and probably some of you remember this came out in JGR Oceans, and Bert had these fold-out maps of these fields at all these different depth levels. And I was trying to find it in my office, but it's so long since I've looked at any hard copies of journals, I couldn't find it. But I wanted to include this picture. This is, Bert here and Warren and Mary Washington. And as you know, he passed in 2018. He was my postdoc advisor. And this was likely taken at a CESM meeting. So Bert provided Rick Smith, John Dukowitz, and Bob Malone, he provided that POCM code to them, and then they parallelized it, as well as making some other adjustments, John Dukowitz to the barotropic solver, and ran it on the CM2 connection machine. And that produced this roughly nominal 0.28 degree near global 20 level pop simulation that Matt Maltrude, who was a postdoc at the time at Los Alamos, and myself, a postdoc at NPS, we were both analysing it. And then soon after that, Rick, and Frank was involved in this effort, the 10th degree 40 level North Atlantic simulation was run. And of course, this was, 10th degree, doubling the number of sea levels. There were no partial bottom cells at that stage. But the goal was to try, and the interesting thing about this was looking at the first Rossby radius versus the grid spacing of the earlier model, the 0.28, and it was resolving the baroclinic Rossby radius up to about 50 degrees north, give or take. Why is it not going forward? Oh, it's got a mind of its own. Okay, so this particular 10th degree North Atlantic simulation was considered a great success, and part of this was the representation of the northwest corner. And what I'm showing here is figure 9 from the Smith et al. Paper, in which Frank was a co-author. And on the top left-hand side, you're looking at mean Eulerian velocity on a density surface from Rayfos floats, just showing the northwest corner up there near the Flemish Cap. And then over on the right-hand side, you're seeing it from the 10th degree versus the 0.28. So the 10th was obviously doing a really good job, and people were very excited about this and saying it's so much better than the 0.28. So that sort of led to a number of different efforts. ONR and DOE were funding an effort then to produce a 10th degree fully global run, and Frank had engaged with the folks at the Earth Simulator, and he actually came out and spent his sabbatical year where I at the Naval Postgraduate School working with myself and Bert. And Matt and I produced the 10th degree simulation, and Frank at the time was also working on looking at doing sensor parameter studies over on the Earth Simulator. And Frank was commenting that this really represented a regime shift when we got the grid spacing down to 1/10 of a degree. But we got started with this run, and one thing that happened was that we soon found that we had the overshoot at the separation point off Cape Hatteras and what we'd seen in the lower resolution models. And that caused some stress because, I was going to ONR reviews and people were asking why was this happening. But we found with time, maybe 10 years into the run, that we started to see an adjustment, and that actually improved. But, we also still, I think, had problems with the northwest corner. So I think, Frank, some time went on. And Frank and Matt Maltrude, and I think Cinta Peacock, were involved in designing what was before had been a dipole grid with the grid in Hudson Bay. They redesigned Frank redesigned the topography to this tripolar grid with the hope that that maybe that would improve some of these issues that we were seeing in the North Atlantic. And also, I believe you put in partial bottom cells at that stage. So I think they did a 100-year run with traces in it. And then, of course, the questions, and the other question with getting the hole out of Hudson Bay was because we wanted to start doing fully coupled simulations. So, that was important for SE interaction. So the next step was that there was this 10th degree pop 10th degree sea ice, same grid, and then CAM 3.5, FV, and CLM 3. And I think there was a half degree CAM and the quarter degree CAM simulations. And then the highest resolution in all that was a collaborative effort between the DOE labs, NCAR, and myself at Scripps. So the ocean and sea ice were 10 times the standard climate model resolutions. So we were, looking to see a broader range of weather scale phenomena and mesoscale eddy scales. Okay, so this was work that Frank led, and this was taking, first of all, the standard 1 degree model up in the top in the left-hand side, and then there was a comparison that was done then between the temporal correlation of high-pass filtered surface wind speed with sea surface temperature. And the best correlation was seen between the, we've got the 10th degree model with the 0.25 atmosphere. So, which was here and here. But if I remember quite correctly, and I think you can see most of the difference between that and the half degree atmosphere was just, it's not major, and it was mainly in the Southern Ocean. Okay, so this was, and then a paper that I led and was, this run that we did for the quarter degree atmosphere, 10th degree ocean, we only ran it for 20 years due to biases and various availability of resources, etc. So there were some firsts in this, and from the Aviso eddy tracks, we had found always with these forced pop sea ice runs, 10th degree, that with a dipole or tripole grid, that the eddies would just continue their way across the basin that was not consistent with the observations. But once we did this coupling with the high resolution atmosphere, we found that we had much more realistic paths, and I guess the argument would be that the SE interaction was causing the eddies to spin down somewhat. Anyway, other people took this up later, Renault, and they worked to this area and significantly advanced these results. Okay, and then we also found that we had a category for hurricane, and I won't go into much of the details, but that was perhaps the first time that had been seen. And then others, again, have moved on. This is from the IHESP simulations that were using a similar resolution components. And they had a high resolution 10th degree ocean, quarter degree atmosphere, and this is a comparison of cyclone tracks from observations, the high resolution model and their low resolution model. And that also involved a number of NCAR scientists. Okay, so this was a project that Bill was involved with, which I had found really interesting at the time. I think this was a nested model simulation because, of course, we're not, in the 10th degree, we're not resolving mesoscale eddies properly. We might be slightly eddy permitting. But this paper, when it came out, it was just showing the, when you were down here, I think this was a 4-kilometre regional model in a 3rd degree North Atlantic setup. And it was just showing that just the richness of the eddy fields in the Labrador Sea and how eddy heat fluxes associated with these eddies generated in the boundary currents were involved in the initial restratification in the deep convection zone. So I got really interested in the issues related to land ice melt. And, nobody was going to put an active land ice model in POP at that time, but there are observational informed estimates that we could add. So what I did here with an interest around Antarctica and around Greenland was to configure a new global simulation that basically around Greenland, the resolution was about 2 to 3 kilometres versus 6 to 7 in the 10th degree, and about 2 to 4 around the Antarctic shelf. And of course, around Greenland, we put in Bamber, and then Teresa Morrison was my graduate student at the time, and we, rather than doing a standard distribution of land ice melt at the surface, she put it over the top 200 metres of the water column. And of course, in this case, we're generating eddies, and we really found a number of, how am I doing on time?
You have about 3 minutes.
Okay. So we did this, we basically had a control with no, this is the West Greenland shelf. We had a control with no meltwater, and this is the schematic of looking at what the density structure looked like. And then we distributed it either at the surface. We did the runs, the sensitivity runs were about 2 to 3 years, and then over 200 metres of the water column. And then what we found was an increase then in the West Greenland current speed in both cases, but more so in the case where we distributed over the top 200 metres. And we found that the greatest freshwater transport then was in the case where we distributed over the top 200 metres of the water column, and the mechanism for the offshore transport was enhanced baroclinic conversion eddy due to eddies, whereas in the case at the surface, which of course this release at the surface is the standard approach in forced models, it was increased Ekman transport. Okay, so I've just done a review here of a major sustained effort over the past decades to model the mean circulation at horizontal resolutions in which mesoscale eddies are explicitly permitted or resolved using Bryan and Cox-derived ocean codes. You know, it's more than just the eddies, it's also doing a better job with the bathymetry, as you know, Eric was talking about earlier. And throughout this, Frank has been involved in many different efforts. He's been either actively involved in formulating models and working with people to analyse them, or providing mentorship to my graduate students. So, you know, he's just been integral to this whole process of getting us to where we are now. So, and his keen scientific insight, you know, it's really benefited all of us in the immediate motion modelling community, but also in the broader physical oceanography and climate communities. So thank you, Frank.
Any questions for Julie? Frank?
What did I forget?
Just wondering about the high latitude land ice ocean coupling and how you see that evolving, whether it requires us to look more directly at coupling the glaciers directly to the ocean. I mean, it's not just that the water is leaving the ocean, the heat is reaching the glaciers, and that, you know, that baroclinic overturning circulation you were showing is transporting heat up the fjord to the glacier as well. And
but you've been working with, we're working on that paper with the box model and the MIT GCM simulations.
Still kind of a one-way thing, though. Yeah.
Right, that's true.
Yeah, I think that's a growth direction for us.
Sorry?
I think that is a near-term growth direction for us.
Yes. Andy.
Yeah, just on that, I was wondering if you've done any experiments where you've had wider shelves or narrower shelves, because of course we have similar processes going on at the other end of the globe, and there's some regions with really wide shelves, and in some of our cases, putting more fresh water on the shelf actually enhances the barrier to water getting on the shelf. And I don't know if that's a function of the geometry or the background state, but I was wondering if you played with the geometry.
The answer is we did not. This was an incredibly expensive run, so we configured it as realistically as possible, and so the answer is no. But We do have a 10th degree simulation, so it would perhaps be possible to compare.
Any other questions? Okay, our final speaker before the break is Steve Jane from Hui.
Thanks. Yes, thank you for inviting me. I'm going to talk about, since it was Frank's retirement, I thought I'd give it a grand title for this talk. Frank Bryan and the rotation of the Earth. This is actually the problem that I ended up wanting to come to Boulder to work on initially. When I was a very tired grad student in the joint program at MIT, I got really interested in these problems related to how the Earth wobbles and how it rotates. And it was kind of tangential to the stuff that was in my PhD thesis. And Carl Wunsch told me to get in touch with John War at University of Colorado. So I did, and told John about my interest in this, and he said, well, that's great, but we're not working on that right now. But he said, come anyways, and I'll have you work on this new satellite mission that's coming along called GRACE, which is actually what I ended up working on. And I'll talk about that here in a minute. But I figured I'd start with this since chronologically comes first, and that is, so there's this wide class of problems in geodesy, which is that the Earth system as a whole has to maintain its angular momentum balance. And there's a trade-off, or a trade of energy, of momentum between the solid Earth, the atmosphere, the oceans, and water mass. That has to, the sum of all those momentums has to equal the same throughout time, with the exception that there's a small loss due to the tides acting on the moon and the sun. So the Earth is slowly slowing down due to the tides, but the rest of it has to be maintained. But if you actually look, so this is the length of day as measured since the early 60s through now. There's a couple things. One, there's this long-term trend in the red, and along the line, so this is microseconds along there. Oh, sorry, the red line is in seconds, which is over on the right-hand side. The residual from that is in microseconds, which is the gray and green lines. So you have this slowing down, and every so often you get these little red dots along the line, and those are leap seconds. So there's this problem that computers don't like the actual Earth system because the Earth does things like speed up and slow down, whereas financial transactions like to happen on a regular 86,400 second sort of thing. And so to keep universal coordinated time and the actual Earth synchronized, you have to do these leap seconds along the way. And so this was pretty understandable. It kept going and going and going till now. And I'm not actually going to talk much about this, but this is a problem because there's a lot of worry that this is going to start going down, and you're actually going to have a negative leap second. And this is called all sorts of hand-wringing. And I'll come back to there's this paper that came out in Nature just in March, a global timekeeping problem postponed by global warming. And there's lots of questions about why it stopped, why the secular trend in the length of day has stopped, and if it is actually going to reverse. Because a lot of the systems, timekeeping systems on computers and the financial transactions that rely on them kind of assume that you're just adding seconds occasionally. But none were built for a negative second. And it's a big problem when your financial transactions happened a second ago, right? So because the order of time shouldn't go backwards. So, so this is a problem, right? No, I'm not blaming Frank, but I mean, sure, we can blame it on Frank. He's retiring. So that's why I said there's still work to do. But so that's a long-term trend. And I actually do think on the subject of this kind of flattening and the turning over, this is something where the climate models can really try and understand this problem and do some kind of prediction forecast of it. Because that's the only these fully coupled Earth system models have all the, you have to account for the atmosphere. It's the whole atmosphere too. It's the stratosphere actually has an impact on the length of day. The ocean has a smaller effect than the atmosphere. But then also there's land ice and sea level change and post-glacial rebound. All these factors are, all of geodesy is wrapped up in this one problem. And it takes a lot of, to figure out what the, how to get this balance to close. And we haven't closed it yet. So the majority of this other signal, which is in gray and is the one-year averages in green, is primarily the atmosphere. As the seasons go and weather systems come and go, they take angular momentum from the solid Earth and then return it back to the solid Earth through like mountain torques and things like that. But the ocean picks up some of this angular momentum along the way, and then it gives it back through pressure torques on the ocean bottom. So Frank was one of the, there was big interest in this kind of in the 80s and 90s, trying to understand Rui Pani and Rick Rosen were a few people who were instrumental in understanding the atmospheric component, and then Frank wrote this paper in the axial angular momentum balance of a global ocean circulation model, trying to understand what the ocean's role in this. And the ocean's role wasn't as big in the terms of the length of the time of day, but it does actually have a much bigger impact in the fact that the poles also have this wobble that's associated with mass moving around. In order to conserve momentum, the actual pole of rotation moves around as well. So the community that works on this sort of stuff is pretty small, but moving on, it relates to the community of people who got together to ultimately do the foundational work that ended up in what became the GRACE satellite mission, which is actually what I ended up working on when I came out. When I got to Boulder, I was working with John War at University of Colorado just down the road, and then I kind of had this joint appointment where I was going to be working with Frank here. And it was great. I got here, like I said, I was tired. I met with John. John had actually been a postdoc at GFDL, going back to the connection to GFDL. And he looked at me and said, you know, I didn't really do much for the first year of my postdoc. And it was great, because it kind of gave me permission to like take a breath and, you know, kind of de-stress and learn about new things. And by that time, we'd assembled kind of a group to focus on this. And it also meant that I told John that I'd be at University of Colorado Mondays and Wednesdays and occasional Fridays, and I was supposed to be up here Tuesdays and Thursdays. But if I wasn't somewhere, everyone assumed I was at the other place. So no one was actually keeping track of me, which was great. But Gene Dickey and John War were the primary writers of this. I think you were part of this too, Detlef, right? The original NAS report. But anyways, Frank was one of the people who contributed to this, and these it was written up as this was written up as a paper by John, Mary, and Frank, trying to really understand what the ocean and hydrographic impacts on the gravity field of the Earth were, and how you could detect them using GRACE. And ultimately, GRACE did get launched, and what I came out to do a postdoc for was actually trying to like take the model simulations and simulate what the GRACE satellites would actually see. And I was working on that. Isabella Vellaconia was working on atmospheric impacts on the GRACE mission, and Craig Tierney was also working on this. And Sean Swenson, we were all in there together trying to decipher if we took all these models, simulations, and tried to actually understand what the GRACE satellites would see, what we would get. And we were doing pretty good. We thought we really understood it. And then Detlef will be more familiar with this. We realized we got into trouble in the ocean. And that is, Craig wrote a paper, and then Detlef had a very parallel paper. And that was in the ocean up here, there's a lot of short timescale variability that's barotropic that we really didn't, we'd had hints of it. Li Fu and Carl Winch had put a panel on a paper about one of the POP simulations, but didn't really remark on it much. But then it was realized that these areas of high short-term variability, and by short-term I'm talking less than 20 days, I think is what this particular map is of. That as your satellites are going over this in a very irregular way, the way GRACE did is you'd be sampling these things and you were aliasing. It would create a severe aliasing into the global mass fields, and how you dealt with them. And it's taken a long time, but eventually they did get mostly modeled out. But it's been, the ocean was the smallest component of, or is the smallest component of the GRACE measurements. And it really did kind of take a while to get to the point where we could remove these impacts. But Frank's contribution to this initially was really understanding, like I said, the impacts of how the GRACE observations actually observe the Earth and what that means when you get these gravity fields of the Earth. So down here, this is a time stepping month by month through the gravity, this is the equivalent in ocean signal in centimeters of water. And you can see there are these very large variations in what is equivalent to the bottom pressure of the ocean, because the integrated mass of the water column is what the satellites see, and that's equivalent to bottom pressure. And then I worked on this, but as well, but to kind of wrap this all up in a nice plot is you measure the ocean through the satellite altimeter, which gives you sea surface height. But part of that is the thermal expansion of water due to heating, which doesn't have a mass. So if you take your sea surface height and you remove the contribution due to steric change using Argo observations, that should match what the GRACE satellite sees in terms of integrated ocean mass. And it's basically you're trying to close this balance. And what you can see over here is it's actually doing a really good job. These are, the blue is the altimeter minus Argo. This is in terms of millimeters of sea surface height. And you can see this big secular trend from about minus 15 millimeters to plus 20 millimeters over time. So 35 millimeters, 3.5 centimeters of sea level change over this roughly 15-year record. And that's the secular change that we're seeing in sea level rise, and measured by GRACE. And there's questions, or by satellites. And there's this question is, you know, is it accelerating? Is it getting faster? I think time will tell. Well, time will tell. I know time will tell. But these are big questions that are still hanging out there in terms of what the future of that curve looks like. But then plotted also as well as different measures of the, or estimates from the GRACE simulations. And you can see they match, you know, pretty dang well through time. So I consider this, for an oceanographer, the greatest result from GRACE so far is the fact that we can independently verify the sea level change from altimetry, Argo, and GRACE. And just to wrap up, Frank was foundational in all of that. So those are my remarks.
Any questions for Steve?
terms of this hiatus or reversal of the secular trend, I haven't read the scientific papers, but there's been popular media coverage of apparent reversal of the Earth's core. Is that a potential contributor here?
There is, so yes, there is the discussion of how quickly the inner core, since it's free, it's solid, and then there's a liquid outer core. So the inner core has this mutation, it's called, where it can seemingly speed up and slow down relative to the outer part, and that's hard to measure, right? They do it through these ideas about how quickly seismic waves propagate through the Earth. So that's one of them. It's thought that the loss of land ice might be another, but somehow it's this ice skater problem, right? You're pulling in your hand, so the Earth is trying to spin faster. So how that, if the inner core is slowing down, that means the outer Earth is speeding up. I mean, it's a hard problem, and it's not solved.
So the slope of that red line seems to change around the year 2000. So is it known why that happens?
No, for the same reasons that we don't know why it might turn over. Yeah, there's other things. The Earth does have these changes that people don't really understand in the shape of the Earth as well. It's called J4, which it relates to the kind of size, but it's really an open question. It's like why there are these changes over time. There's other periods. There's the moon isn't exactly aligned, so there's this 18.6 year oscillation because the moon kind of does this through time on an 18.6 year time scale. So the question is that the cause of some of these changes? If you remove these secular trends, you do kind of see this kind of 20-year thing.
Do the Milankovitch cycles have an effect on the rotation?
Not at this short a time scale.
Yeah,
I mean, the Milankovitch cycles are much longer.
So I had a quick question. Do they add regularly, like every year 1 sec, or what? But it's every year it changes,
every couple
right?
of years, yeah, it changed through time. We didn't have one for, there's a break between 99 and 06, but the International Earth Rotation Service, there's an International Earth Rotation Service, keeps track of this, and they make a recommendation.
I'm glad somebody's keeping track of it.
To keep, like said,
sleep
universal
easy.
coordinate time has to mean the same thing to everybody.
And then can they add for financial people, I guess, I mean, it's always plus something, but can they add a negative number?
Well, that's where things get bad, right? Because if you're doing a financial transaction and it happened, you say then, oh, it happened a second ago.
You can make money.
You could make money. But they don't, the proposal is actually just to stop doing leap seconds altogether. And slowly universal coordinate time and Earth time, the time that the sun's at noon, will slowly drift apart.
Is it easier to add 0.999 of a day or subtract a second?
Yeah, I don't know. I'm not in the business of keeping time for the world, but it is a similar problem, right? We did this experiment, 1,000 years ago when we had no leap days, right? And eventually things went awry and we were a couple months off. So everyone got together and popes were involved and they created something with a very strict set of leap day ideas. But
we need an asteroid impact.
Yeah, exactly.
Frank is saying that we need an asteroid impact. Any other questions before we take a break? Okay, if not, let's think again, Steve. So we'll come back at 3:30, and Ian is the next one.
you open this?
This is the file.
So they're definitely in the Google Drive.
He said he downloaded right after lunch.
Oh, they may not have updated here, though. That's the thing. I think they have a different. No, it's not there. Because they have to transfer it. You can't just download here. There's a transfer mechanism. So.
The browser was open and you could.
Okay, before we go down to only one person's remaining in the room, or maybe two people remaining in the room, it's getting sparser and sparser as people leave. So this is our last session. So we'll have Ian, and then we'll have remarks if anybody wants to say anything, and then we'll conclude with Frank, and then we'll have the reception after that. So with that, our speaker is Ian Grooms from CU. Take it away.
Thanks, Gökhan. This thing work? What's going on? Okay. Okay. No, that's not working either. There we go. Okay. So the work I'm going to present today is over the time that I've been involved with NCAR Ocean Section. And so I've worked with a lot of people here in the Ocean Section, as well as other people, some of whom are also here. And I'll start, before I talk about science, by saying that it's really been wonderful for me to be involved in this community, and I'm very grateful for the opportunity to have been here and been able to work with you all. And you know, it is NCAR, and you're sort of supposed to involve visitors, but it hasn't felt grudging at all. It's been very welcoming, in fact, and people have been patient with me and supported me as I've moved from a young and naive person hoping to be an ocean modeler to someone who's not so young but still naive. Right, exactly. So I won't read everyone's names, but that was Ocean Section, and of course Frank has been instrumental in that as the head of the Ocean Section, getting me set up, giving me a desk right outside his office, which he didn't have to do, and then putting up with me when I decided to walk just across the short space of hallway and ask him stupid questions. So thanks, Frank, for that. So a few years ago, my very first grant ever, stochastic parameterizations in ocean models, didn't get started well. And I was a few years into the grant, and for various reasons, basically hadn't done anything. And I was looking for something to wrap up, something that was feasible, that I could get done with a student, you know, sort of salvage the project. And I talked with various people, including Frank, what is something that, you know, reasonably could be done, and settled on this idea from Jean-Michel Brocard. And this is sort of not your usual parameterization, because usually we're thinking about momentum fluxes or tracer fluxes or something like that. And this parameterization is about the equation of state, and it's not finding a new equation of state, because that's not my personal interest. My interest is parameterization. But the connection to parameterization in the equation of state is that you have a low resolution model, and it's not keeping track of temperature and salinity point-wise. It's keeping track of sort of averaged values of temperature and salinity and pressure on the scale of your grid. And then the equation of state would tell you temperature and salinity and pressure at a point will tell you the in situ pressure at that point. But that's not how we use it in the ocean model. We plug in these sort of averaged values of temperature, salinity, and pressure, and then interpret what comes out as if it was the cell averaged value of density, but it's not, because the equation of state is not linear, so there's an error there. That was actually recognized previous to this paper, but this is the first paper that actually developed a parameterization for it. Okay, so from that paper on the left, here is a diagnosis of the error in density near the surface from, I think, an observational product. And then he developed a parameterization, and the parameterization is on the right, and it's not that good. Like, it's qualitatively correct, but it's not that great, right? And so we decided, okay, we can probably, hopefully, fingers crossed, we can do better than this, right? So we'll try to do this. This is a real effect. When you fix it, it has implications for the model circulation. Let's try to do something better than this. And so that my student was Zofia Stanley. Frank actually supplied us with 10th of a degree pop data from a simulation he did with Ben Johnson, but he actually wasn't involved in this paper. The parameterization that we came up with is really simple. So the rho is the equation of state, T bar, S bar, P bar, those are sort of the cell averaged values that you get in the model. And then the correction that turns out to be really an excellent fit offline is you just do a second order Taylor expansion, and the only term you keep is the second derivative of the equation of state with respect to temperature, and that gets multiplied by the subgrid scale temperature variance divided by 2. And this offline is an excellent fit. Of course, you don't, in the model, you know what the second derivative of the equation of state is, but you don't know what the subgrid scale temperature variance is, so you still have to parameterize that term. And we came up with a pretty simple parameterization of the subgrid scale temperature variance in terms of the resolved gradients. And that part, just the temperature variance, so on the top we have a diagnosis of the subgrid scale temperature variance from this 10th of a degree pop data that Frank supplied, and then on the bottom is our parameterization just of the subgrid scale temperature variance. And it looks, you know, pretty good. It's on a log scale, so maybe it's hard to tell how good it is. But it looks pretty good, I think. On the right is our prediction on the bottom versus the actual on the top. And it's also on a log scale, but you can see that there is spread around the fit, but it's, you know, not a bad fit. So then when you plug that back into the full parameterization, so we plug the parameterization of subgrid scale temperature variance in here and use it to correct the density, we can see how well that works offline. And this is it. So the top is the error in the cell average density at the surface from, I think, a 5-day average of this 10th of a degree pop data. And on the bottom is our parameterization. Now this is still offline, but we are using our parameterization of the subgrid scale temperature variance, not the actual diagnosed value of subgrid scale temperature variance. And so, you know, this, I think, is better than this. So we developed that offline, and then with much help from Alastair, implemented this thing in MOM6. Also help from Phil Pejon for implementation. And had a postdoc, Jessica Kenigson, who also was given a visitor position here and participated in ocean section activities. And ran this thing in MOM6 with much help. I wouldn't have been able to even run this thing. So I needed help to implement it. I needed help to run it. I needed help to understand the output. Couldn't have done any of this without the ocean section. And we found that, yeah, it does make a difference. And of course, this isn't the first time people had parameterized this effect and found that it makes a difference when you run it online. So no surprise that it actually makes a difference. It's not ubiquitous. It doesn't change the circulation everywhere. It only changes the circulation effectively near places where you have a strong temperature gradient that is compensated by a strong salinity gradient with a compensating effect on density. And that's where this parameterization is most active. I neglected to mention that the parameterization that we developed of the subgrid scale temperature variance, the sigma squared term, is a stochastic parameterization. So I'm not giving you details, but fits with the title of the talk. Okay. Okay, and so here's some changes that happen in the hydrography of the subpolar North Atlantic, potential temperature, salinity, top and bottom rows, and then we have a deterministic version of the parameterization in case people are allergic to random numbers. And then we have the stochastic version on the right there. And you can see it changes the potential temperature at the surface and the salinity in the subpolar gyre. We track that down to changes in the flow through Denmark Strait. And in Denmark Strait, there is sort of a juxtaposition of cool fresh waters coming down through the East Greenland Current and warmer and saltier water coming up around Iceland from the subpolar North Atlantic. And so the parameterization is active there. And because it changes the transport there, it changes the hydrography in the entire subpolar North Atlantic. Okay, then it has an effect on mixed layer depth, as you might suspect. If you change sea surface temperatures, you're going to be changing convection and mixed layer depth. And it also changes ice thickness, again, presumably because of the connection to sea surface temperatures. Okay, so in that paper, the only place where we corrected density in the model was in the computation of the hydrostatic pressure. So vertical derivative of hydrostatic pressure is balanced by buoyancy, which depends on density, and so we corrected that. We then went on and put this correction into other places where the model uses density, including in the Jen-McWilliams parameterization, which uses density to compute isopycnal slopes, and in the mixed layer eddy restratification parameterization, which is similar to a GM parameterization, but for the mixed layer. So we put those into the model, we ran it in a forest ocean case, just like Jessica's paper, and it didn't do much. So once again, I was somewhat at a loss and went to talk to Frank and said, you know, we've run these simulations and done these diagnostics, but it's going to be hard to write a paper because it doesn't really make much difference. And he said, well, why don't you run a coupled case? And then we heard from Justin earlier today, this afternoon, the work they were doing with the interaction, air-sea heat flux, ocean intrinsic, atmosphere intrinsic, how much variability is there. I won't attempt to review all of that material. But the idea was, well, maybe in a forced case, you don't see a big variability change because the atmosphere has an infinite heat content and you're restoring and it sort of damps variability. But in a coupled model, the variability that you're introducing might feed back and interact and have a bigger effect. And you could see it in this kind of a diagnostic, which that diagnostic doesn't even make much sense in a forced model. So we did that, and postdoc Niraj Agarwal was able to get a paper out of it, and it does indeed have an impact in a coupled context. And we worked with Frank and Justin and Phil Pejon, who's at NOAA down the hill on that one. So Frank saves the day again. And then we've basically wrapped that up. I'm not really doing anything with that parameterization anymore. The grant has finally died after 2 no-cost extensions. So I moved on, and I'm going to tell you again what I told you about on Wednesday if you were here. So I moved on to stochastic backscatter. So there is actually, the previous parameterization has an element of stochastic backscatter to it, but it's really focused on just changes to density. And in this, I'm really focused on the backscatter itself and a different process, not the density, but the mesoscale eddies, which are stirring around, generating Reynolds stresses that are then feeding back on the large scale flow. So that's what the stochastic forcing term represents in the velocity equation. And we decided to set the amplitude of the backscatter, not in sort of a data-driven way. If you look at the literature for stochastic backscatter for global ocean models. Much of it is sort of data-driven, like here's a high-res model, look at the variability, diagnose some EOFs or something, and then put that back into the high-res model, which is great, but what if you want to run the model in a different climate? Or what if you want to run it, in the last glacial maximum or something? That data-driven approach doesn't port very well. So we're doing a more physics-based approach where we set the magnitude of the backscatter proportional to the rate at which the GM parameterization is removing energy from the resolved flow. And that idea goes back to a paper by Scott Bachman, who was part of the open section at the time. And he achieved that. He had a GME parameterization, but he did it in a deterministic way, not using a stochastic backscatter, but with a negative viscosity. And so we replaced his negative viscosity with a stochastic backscatter, which works a little bit better in a model that has no eddies. So negative viscosity works a little better if you have some eddies partially resolved. If you don't have those eddies partially resolved, stochastic works better. So we implemented this in MOM6 with much help from Phil Pajan and Niraj Agarwal. We implemented it not by changing the tendency of velocity, but by adding an increment to the horizontal velocity in between time steps of the model. 3 minutes? Okay, so many of you have seen this because you were here on Wednesday morning, and unfortunately, I was going to show you some videos here, but despite assurances, they're not working. So I don't have any videos for you. So I'll just review briefly that this has a big impact. So the stochastic equation of state has an impact in a limited number of geographical locations, and it has a salutary effect in those locations, but it's simply not active in most parts of the model because the error that it's correcting is small in most parts of the model, right? One little parameterization should not be expected to fix the entire model. This parameterization is the backscatter is active everywhere that GM is active, and GM is active in very large parts of the ocean. And so this has correspondingly a pretty big effect, a much bigger effect in more areas than the previous stochastic parameterization. I will say that we looked at a lot of diagnostics. What I presented on Wednesday was that it significantly improves the sea surface height variability, the sea surface temperature variability. That's all I showed. We looked at a lot of other metrics that are in the paper that's on Earth and Space Science Open Archive, and it doesn't damage the mean state of the model. It has actually a very limited effect on the mean state of the model. So I wasn't hiding anything there. I wasn't saying, oh, it improves variability and it damages the mean state, but I'm just not going to show you the mean state. It doesn't damage the mean state. It leaves the mean state largely unchanged, and it improves the variability significantly. And so thanks to all my co-authors and to everybody who's been so hospitable and welcoming to me here in the ocean section, especially Frank.
That was a very nice movie, by the way.
Yeah, thank you.
By any chance, do you have the movie in the drive anywhere that Ian submitted this afternoon? Do you see it?
It's in the Google Drive, but it's not on the laptop here.
I think it was submitted this afternoon, you said?
No, I submitted it all yesterday.
Yesterday afternoon. There's supposed to be a movie file.
I don't know if we need to spend time on that.
Okay. Any questions in the meantime? Yeah.
I have a question about the density parameterization. So you focus on lateral temperature gradients, but did you think about vertical gradients, which you couldn't use like a 10th degree pop model? You would have to figure out how to estimate it from a parameterization, but then that would affect n squared, which would affect the parameterization of vertical mixing, blah, blah, blah.
Right. So when we were developing this, we didn't think much about it because the grid size, in the vertical is quite small, and so sort of the amount of variability in the vertical direction that's unresolved is pretty small compared to the amount of variability in the horizontal direction that's unresolved. That being said, I presented this to an audience where Andrew Shao was present. And he, as part of his neutral diffusion algorithm, did a lot of work on sort of representing the subgrid structure in the vertical direction of temperature. And so you could use actually those pieces which are already in the model to say, well, what's the difference between the cell average of temperature in the vertical versus the reconstructed variability, and add that back in. I kind of suspect that it's not going to be as big a component just because the vertical resolution is fairly high.
So a lot of the ideas behind, motivations behind stochastic parameterizations is that by adding that noise in a nonlinear system, you kind of change, say, the mean energy in the system. Right. So it's very curious that you've added variability. So clearly the parameterization is knocking things around, and yet I think you were saying that the mean state hasn't changed much. And so it's like, is that meaning that even at the resolutions you're running, the model isn't nonlinear enough?
I think it depends. So, what kind of noise you add makes a difference, or where do you add the noise? So in our first parameterization with the equation of state, we did see in some places a change in the mean state that we could associate specifically with the stochastic component, because we had a deterministic and a stochastic version, and you could only see the change in the stochastic component, and so there was a rectified effect. Paul Williams, for example, has a paper saying that, oh, if you put in stochastic variability and heat flux at the surface, the mixed layer will deepen, because some of the perturbations don't cause it to get deeper, they just don't do anything, and other perturbations cause it to get deeper, so the net effect is for it to get deeper, right? Even if the noise has zero mean. And it just so happens that I think putting in perturbations to the lateral velocity at these scales seems to be a direction in which the model is not terribly sensitive. There are some changes to the mean state. The transport through Drake Passage goes down by like 5 Sverdrups, but these are small changes.
Hi, Ian. I have a question about your stochastic backscatter. So the mass-scale eddy velocities would be mostly along the isopignal. By adding a horizontal velocity increment in a z-coordinate model, can you make sure that the velocity is still mostly adiabatic?
Well, so the simulation I did was Z star, so we were really doing, lateral velocity along lateral surfaces. I think it would just be pretty difficult to rotate my velocity increment so that it's aligned with an isopignal surface. Well, I will note that even in a model that has surfaces that are not aligned with geopotential surfaces, the velocity is still the horizontal velocity. It's not the along surface velocity. And so constructing on a long surface velocity might be valuable, but I think it would be pretty hard practically to do.
Alistair looks puzzled. Yeah, Alistair says his meaning Ian's perturbations are adiabatic. And Wanda is thinking. Are you okay?
No, I'm just wondering. So with horizontal, if you only enhance the horizontal velocity, you can ensure a adiabatic feature.
Right. It's just in the momentum equation, yeah.
Okay.
I mean, he's avoiding that issue just by putting it in the momentum.
Right. I think Dan Witt asked a question about, could I adjust? So the perturbations I'm putting in are unbalanced in sort of a geostrophic, sort of hydrostatic thermal wind sense, which means they radiate waves. And could I adjust the density so that they're balanced? But then as soon as you do that, you're monkeying with density, and you might not conserve temperature, or you might not conserve heat or salt. And so I try to avoid things that mess with density.
Okay, well, thank you very much, Ian. So now you have the remarks session, and Peter volunteered. So this is open to everybody. It's open mic, and anything that you would like to contribute, you are welcome to do so.
Well, I didn't say much about my collaboration with Frank in my talk this morning. So Frank and I have collaborated on a number of papers, which has always been extremely positive, and he's always been a very strong contributor to that. So thank you for that, Frank. He has also taught me quite a lot about the real ocean modeling, and the oceanographic literature. I think he knew a lot more about the real ocean because he was trained as an oceanographer, whereas I wasn't. And I wanted to illustrate this by a recent example. About a month ago, I was asked to review a paper for the Journal of Climate, which was assessing heat transport due to surface waves, and in particular, due to the Stokes drift in surface waves. And this paper was coming up with transports of a few petawatts. Now, I know that the AMOC transport, is on the order of 1.2 or around 1. So these numbers were, I realized, totally ridiculous. So at lunch on that day, I started to talk to Frank about it, and he agreed with me that those numbers just couldn't be right. So we went out for a walk, as we always do. But when I came back, a few minutes after I got back, I took the paper into Frank's office and showed him the formula that they'd been using to calculate this. And Frank said immediately, that isn't right. So what they'd done is they'd ignored the heat flux due to the return flow of the Stokes drift, which in fact, in the mixed layer, is at almost the same temperature as the SST. So no matter how strong that sort of overturning is, it can't transport much heat. And immediately, Frank knew of two references where the original one was by Ray Montgomery, as of the Montgomery potential, pointing out another paper where this same mistake had been made. And a paper by Klaus Bonning on when he talks about what temperature to talk about for the return flow. So I went back to my office, and within 10 minutes, these two papers appeared in my email, so I could read them. So this is an example, I believe, of Frank's immense knowledge of both ocean modeling and the literature. And of course, what it did in the end was it really, really improved my review of this manuscript. So I think this is just a small example of the contributions that Frank has helped me make to the field. So thank you, Frank.
I'm hoping that the co-authors of that paper are not here. Gustavo, do you want to? Sure. I can put your slides up.
My comments are on similar lines as Peter Jane. And if you ever be on the 4th floor, chances are you've seen Frank reading a manuscript on his desk. And he often he has a desk that faces the Flatirons. He always uses that desk to read the papers. So if you've been on the 4th floor, you've probably seen this. So I intended to take a picture of the last few weeks of Frank doing that, and I was not very successful. So at lunchtime, I asked ChatGPT, and my prompt was sketch of a scientist reading a paper about ocean modeling. And that's what it came. And I put Frank's face. And that was the first drawing. And then I gave 2 additional prompts saying, remove the ocean views from the window because it was mountains. And then it gave me the same picture. It didn't change. And I also said, remove the computer from the desk. And then it didn't change. And afterwards, I was like, okay, I had to leave. it's, well, first of all, Frank likes surfing, so ChatGPT knows that, and that's what he's looking forward when he retires. He'll be able to surf more, which is awesome. And the computer is reminding me that Frank learned Python not long ago. I think in the last 5 years, he switched to Python. And he will say, oh, I'm not very good at Python. He's amazing at Python. He codes really well. In fact, most of the time we show ocean diagnostics for MOM6, a lot of the plots come from Frank. So ChatGPT also knows that, so he kept the computer there. But I did manage to take a picture of him. He's not diagonal. He's not at the perfect side, but he usually was on the other side. But no, that was the picture. It was right after lunch. I don't know if he's reading or sleeping, so that's why I asked ChatGPT. So thank you so much, Frank, for your leadership and for, as Mike said in the morning, like for being inspirational for us of the fundamentals of science is to going back and reading these papers. And this is the backbone. Like you've always, every time you have to write a proposal, to write a code about anything, or even do the World Ocean Atlas to look at initial conditions, you go to the backbone, you get the paper, you take the time, and I find that amazing. So thank you.
Actually, I'll just continue with the same thing because I was gathering my thoughts as to what I would say during this session. I've been here more than now 32 years, and Frank has been one of my mentors throughout those years, and I learned a lot from him. So two things that, very impressive about Frank is exactly what Peter and just Gustavo mentioned. He is immensely knowledgeable about oceanography, ocean modeling, and literature. You go to him, ask a question, not only he knows the answer, then he goes to, he's amazing that keeping all of the papers in the, those drawers now. We don't have the original signed copies now with the co-authors. So he has an amazing literature. In fact, when I ask him a question, if he can't find the paper immediately, within an hour, the paper shows up on my desk, essentially. So that is one. And then the second thing is quite impressive is his writing ability. And whatever he writes is very thoughtful, considering everything. And I'm just impressed beyond whatever the right word is. So those were the two things that I wanted to convey, in addition to everything else that people mentioned throughout the day. So thank you, Frank. Any more remarks? Keith, maybe we should pass the microphone.
I'll start off by saying what they said. In Gustavo, you stole my thoughts exactly. That when you walk by Frank's office, this is often the image that you get, is that Frank is immersing himself in the literature constantly. He's always learning. He's always trying to improve his knowledge. And I find that inspirational as something to, it's a high bar to try to reach that sort of dedication to learning the field and staying up to date in the field. And he sets an amazing example with his actions. Another aspect of Frank's leadership that I wanted to highlight here is his steady hand and his steady approach to challenges that the ocean section has faced over the years, or people that Frank always approaches things and is very level-headed about his approach to dealing with different situations. And again, I find that as a great example of what leadership ought to be. And it's something to aspire to. And thank you, Frank, for your leadership.
Any other remarks? Too late after a 5-day meeting. Don't worry, I moved the reception earlier to 4:30, so you don't have to fill the... Okay. Many of the people already mentioned in the room, in their presentations, so... Okay. Frank. Frank is going to now remark about Frank.
You get slides? Okay.
I'm going to say that, I don't know, whatever, 6 months ago or so, when Gökhan and Gustavo were asking me whether I wanted to do anything on the occasion of my retirement, I said, no. But it is the 50th anniversary of the ocean section. Let's do something for that. And they slipped in the retirement part too. So, but thank you. It's been a really fun day. And I know it's been a hugely exhausting week for you two. It's quite an accomplishment to bring 100 people here to Boulder and create such an engaging conference. So thanks for that. Yeah, so in February 1959, 6 months after my birth, a committee representing 14 universities submitted a white paper to the National Science Foundation to create a National Institute of Atmospheric Research. And it lays out the rationale for doing so, what kind of work would go on there, and what the characteristics of that institute might be. And I think, and it's sort of captured in these 4 points, and I can't imagine a more ideal environment to do science than what was laid out here, and what NCAR has actually lived up to. Who can ask for anything more than to be able to work with the best minds in the field, be provisioned with amazing resources, to work on hard problems over extended periods of time, and engage with our community of colleagues. And for that, I'm just phenomenally grateful to have been able to participate in that. And I thank my lucky stars every morning when I walk below the bronze letters on the front door. It's been a true privilege. So I want to, and it's the colleagues here in the section that have made that such a rewarding experience. And I want to thank everyone who's ever been in the section for for their contributions to that. But I especially want to thank Bill Holland and Peter and Bill Large for their mentorship and unreasonable patience with my, Gökhan said I write well, but I write really slow. So anyone who's looked at my CV will recognize there's an enormous gap following my postdoc. It really took me quite a long time to get my traction and get my science rolling. And they extended, as I said, unreasonable patience and mentorship getting me through that. As I said, I'd like to thank everybody, and as a community center, we've as Ian said, we're sort of expected to work with the community, but that's really what I thrive on, is our interactions. So thanks to everyone in the community who we've had the opportunity to work with. But I do want to mention 3 people who I'm really grateful for the way that they've influenced my career in particular times. The first is Klaus Bühning, who you heard about several times this morning. As Detlef and Julie and others described, we were engaged in this modeling activity as part of the WOS program And we built these models. They were pretty exciting. They didn't look like the 1-degree models, but they still weren't that realistic. And I was personally struggling. A lot of the modeling community loved them. The observational community just thought they were ridiculous. We didn't get a lot of buy-in from the rest of the WOS community. And I was struggling with trying to figure out what science I was going to do with this thing. And it was really Klaus, coming from the deep observational background in Kiel, sitting with the observationalist, that he really put together a research program for us and some relevant questions that we could address with those models. And that series of papers we did together really kind of broke the dam for me and got my science rolling. The second is John Warr, who Steve was talking about. I actually met John. We overlapped at Princeton for a matter of hours. Literally the day I arrived, I was taken around to meet everybody in the building, and John was packing up his office to move back here to Boulder. He had done a postdoc with Bram Oort and Tony Dolan in geophysics. And so, he was here in Boulder, in Princeton, and while it wasn't part of my thesis work, I did do research with Bram Oort, who came from the STAR School of MIT. We're just thinking about really basic fundamental properties of the Earth system and working through the balances and learning how to use measurements in one part of the system to make inferences about another part of the system. So things like the angular momentum budget, and the energy budget, and the water cycle. So anyway, I really developed an appreciation. My first scientific publication was with Bram on the global hydrologic cycle. So I really developed a deeper appreciation for that kind of work. And sort of came here, got involved in high resolution modeling stuff. That was not part of my agenda at the time. And then through a sort of random set of circumstances, I met another geodesist here in town. How many people knew they'd measured G at the Table Mountain Observatory 10 miles north of Boulder? Like every day they drop balls and measure G. But anyway, I met this guy, Doug Robertson. He was talking about, there's these problems in polar motion. We could do something with an ocean model. And through him, I met John, and we developed a really productive collaborative relationship with John's students and postdocs, including Steve. And that was a really rewarding scientific period for me. And then finally is Rick Smith. As part of the work in geodesy, at that time we were working with this early sort of pre-MOM version of the GFDL model, which was a rigid lid model. And a lot of the geodesy problems are really interested in the changes in the moment of inertia of the Earth. And it didn't work in a rigid lid model. It didn't go anywhere. So I needed a free surface model. And at a WOS modeling meeting, I think it was a WOS meeting in Los Alamos in 1994, so I remember the year because the meeting was a few days after Catherine and I got back from our honeymoon. So we got back from Africa and I took off, said, back in a week. Anyway, I met Rick and they were running these high resolution global models on the connection machine. And so I was talking with him about the possibility of using that data. He sent me a bunch of data, I was using it. And eventually, we became really good friends and collaborators. And I started, at that time, NCAR had acquired the Cray T3D, which is a really early distributed memory machine. And it's sort of like GPUs now, there's nobody using it. So I could use as much time as I wanted. And so I got POP running on the T3D and started running it myself and was using it in these sort of applications. And over time, it really, as it was clear we were going to be using distributed memory machines, it became a pathway for us with the CSM as our ocean component model. And Rick became a really central part of that transition for us, became the co-chair of the Ocean Working Group. He was really a huge contributor. And it's, was really a tremendous loss when he became disabled and wasn't able to work with us anymore. So I think those three people need special acknowledgement for steering my career at certain points when that made a really important impact. So I think, right now, we've over the last really 30 years or so developing CSM, we've had a really clear goal in CGD. And right now, I think we're sort of in a transition period. We're trying to figure out what our collective goal is. And so there's a sort of a number of transitions going on. Society as a whole, there's a different public expectations for what kind of science we should be delivering. NCAR is going through some transitions with how we fund our science, how we make scientific appointments. And there are big transitions in the field that we've heard about this week. New techniques in AI and machine learning and how those interact with our physical modeling. And that is a lot of transition for an ossifying brain to deal with. So I think it's time for me to sort of step aside a little bit and follow these bright young guys rather than trying to lead. And I think I'm really confident that they'll be able to move us through this transition in a positive way. So people have been asking me all week, what are you going to do? And so the answer is, in the short term, probably pretty much the same thing I have been doing. I know I owe several people in this room manuscripts or edits of manuscripts, so there's a lot of that to get done. We've got to get CSM3 out the door. A lot of work to do there, writing those papers up. Anna-Lena mentioned, this TPEX experiment that we've been working on, helping design some of the sampling strategies for. That is, there's a call out right now for people to propose instrumentation. So I'm sort of looking forward to seeing what happens there and seeing in what ways I might be able to help with the synthesis of those data sets. And if Melissa gets the Cape Falcon experiment funded, I'm on it. Yeah, and
Are you really retiring?
well, yeah. So I guess the other career is trim carpentry. 11 years ago today, this was our basement, the big 2013 flood. And our finished living space in the basement turned into unfinished art space for Catherine. So over the next couple of years, I'll be turning the basement back into livable space, learning how to be a carpenter. Other than that, as Gustavo mentioned, I enjoy surfing, and we have a place out in Oregon. And I think whether that experiment's funded or not, I think we need to establish a long-term monitoring program there at Short Sands Beach. It's my favorite surf spot in Oregon. So that's it. So again, thank you to everyone for a great day and for a wonderful almost 39 years now here at this incredible institution. So hopefully the beer's cold by now.
Okay, so now we can go to the cafeteria and have some whatever beer, wine, and food. And again, thank you for joining us on this special day, both for Frank and for our section. Thank you very much.